Okay, welcome to the Claude Certified Architect exam preparation course. My name is Ahmed Fathi and I will be your instructor for this course. So, how is this course structured? This course is structured around efficiency first. So this course is designed for technical engineers with little time to waste. Focus is on getting to the point as quickly yet as thoroughly as possible. So this course is also question based. So for every lecture, we will start with a realistic exam question, explain the question and the answers, explain the new concepts in a thorough and effective way, including some code examples, then answer the question, then repeat. Okay, this means that earlier questions will be typically simple, but they will take more time to answer since we are going to be introducing new concepts. Then progressively, questions will become both trickier and also faster to answer. So who is this course for? So this course is for engineers willing to create agentic systems and workflows, engineers willing to pass Anthropic's CCA-F exam. However, this doesn't mean that if you don't care about the exam, this course isn't for you, because this course is still going to add valuable information to you as a workflow builder. And even if you don't really care about Claude itself, I would say that the architectural knowledge and decisions and insights apply to all vendors. So prerequisites, you need to understand programming, especially in Python. You need also some basic understanding of LLMs, nothing fancy. And finally, this is my LinkedIn profile. Feel free to connect with me and see you in the next video. Okay, so now with question number 1. You want to build an application that uses Claude to answer customer questions. You need to choose between two approaches. The first one is using Claude through the Claude.ai website, or 2, using the Claude API. What is the primary advantage of using the Claude API instead of the web interface? And then you have 4 possible answers. So the first one, the API is free while using Claude.ai requires a paid subscription. Option B, the API allows you to programmatically send messages and integrate Claude into your own applications, while Claude.ai is only for manual chat. Option C, the API has more advanced Claude models than Claude.ai. And option D, the API doesn't require an internet connection. So obviously this is not a question you will find on the exam. I'm just trying to start with very simple hypothetical questions so that we can actually introduce concepts. And the concept I would like to introduce in this video is the Claude API. Okay, so what is a Claude API? So in general, all major players in the agentic AI space provide APIs to call their models like Anthropic, Claude, DeepSeek, Gemini, ChatGPT, Grok, and so on. And API stands for Application Programming Interface. So really this allows you to call the LLM from code. So your customer or your end user doesn't necessarily need to see a chatting interface at all. Still, they get the intelligence. So, for example, you can have some non-player characters or NPC characters in a game, and those characters can actually be mind-controlled by an LLM in the background to take decisions. So there is no chatting here, but the LLMs are actually controlling the actions of those characters. You can, for example, also create a budget app for users that automatically categorizes purchases based on scanned receipts and tries to classify them into like different categories. So again, this can be done using an LLM in the background. Okay, so you can think of an API as a typically stable interface or contract between you, like you are the application programmer, and Anthropic or the Anthropic's team building the models. So the API itself should be reasonably stable, like the function names and parameters and so on should be reasonably stable. And the inner implementation details can be changed by Anthropic without affecting the API. For example, you shouldn't really care if Anthropic is running the actual inference on NVIDIA GPUs or on custom chips. You just want to submit a request and receive a response, right? If Anthropic finds a super clever way to do something fancy like increase inference speed or something, you get that for free without changing anything in your code because you are programming to that API, okay? So this is an example API call for Anthropic. So this is Python obviously, and then you can import like Anthropic, and then you create a client using Anthropic to Anthropic. You obviously need an API key that you get again from Anthropic by registering. And then you can do something like client, which is this one right here, .messages.create. So this is the Claude Messages API. And then you create a message. You choose your model like Claude Opus 4.7 or 4.8 or Fable or Mythos or whatever. And then you send a message. And this is the content of the message, hello Claude. And then you receive a response as a variable. And then you can just print that response. So there's no chatting interface, okay? So API changes are actually allowed, but they might cause some compatibility issues. And this is why API versioning is important. And in a fast-paced environment like the agentic AI space, API changes are actually to be expected. So the concept of an API is not really limited to LLMs, but also it is not limited to cloud-based services. You can have an API call to a local model if you have that set up using Ollama, for example. Okay, so now back to the question. The answer is obviously B. The API allows you to programmatically send messages and integrate Claude into your own application, while Claude AI is only for manual chat. This was the first question. See you in the next lecture. Okay, now question number 2. A lead AI engineer is architecting a multi-agent system for a financial firm. The application must perform an initial data extraction, pass the data through a verification loop where a critic agent reviews the coder agent's output, and finally ensure that the results are returned as a strictly typed Python object to prevent downstream database errors. Okay. The team decides to use a modular stack involving the Claude 4.7 or 4.8 Opus model, PydanticAI, and LangGraph. Which component is primarily responsible for managing the state and the iterative critic coder feedback loops? LangGraph, LangChain, Claude API, or PydanticAI? Okay, so to be honest, this question is unlikely to appear in the exam. The exam is focused on Anthropic. It doesn't really care about LangGraph, LangChain, and PydanticAI. However, I think you need to understand those different philosophies or those different libraries in order to do proper workflows. Because in your job or in your workflow, you actually need to choose which of those to use, okay? So if you can't explain the difference between those four, you will struggle in a real world production scenario. So let's try to develop a simple but clear mental model on what each of those libraries and frameworks specialize in. Okay. So LangGraph. LangGraph is an orchestration framework. So think of it as a tool or a library designed to make building and managing state machines in code significantly easier. So because it is fundamentally a state management engine, you can build applications with LangGraph that involve no LLMs at all and still benefit from its robust architecture. For example, it seamlessly handles state transitions, conditional branching, forking, joining, parallel execution, and iterative loops with built-in retry logic. So basically in LangGraph, you have some sort of a state, a unified state, and then you have some nodes and edges, and you pass this state across those nodes and edges based on some conditional logic and so on, and then every one of those nodes can actually change the state, and then finally you get something out of it. So that's on a very, very high level. You don't really need to use it with LLMs at all, and this will become clear as we progress. So in LangGraph, you define computational nodes and you also define edges. So nodes are the units of work. The simplest form of a node is a standard Python function that executes logic. For example, it receives your state object, does some changes, and then outputs that state object. Okay. Now, edges represent the pathways that determine the flow between the nodes, and we will see some examples soon. So inside those nodes, you can, but you are not required to, call an LLM API like the Claude Messages API that we talked about in a previous video to perform reasoning or data extraction, but you can just have some very simple mathematical equation, for example, if you want. Okay? So LLMs typically run in loops. Like, think of a coding agent if you are familiar with Claude Code or Copilot, which you should be, obviously. But you can actually remember those coding agents saying something like thinking and then reasoning and then, let's say, calling some tool like grep search or something, and then taking the result of the search and then doing something, and then passing those information or this information into the context of an LLM API call, and then receiving a response from an actual LLM, and so on. So I mean, this is a very dynamic flow, right? And you can create those flows using something like LangGraph. So agents need to reason, plan their work, make code changes, run tests to validate, find mistakes, and then reiterate to find better solutions, and so on, right? So typically the main or the orchestrator agent can also start sub-agents to do more specific work, and we'll talk about sub-agents a lot in this course. But again, if you just use Claude Code or Copilot, you'll find those sub-agents actually sometimes automatically being spun up, right? But if you are creating your own LangGraph, you can create like a repo reader sub-agent, a code modification sub-agent, a code reviewer sub-agent, a research sub-agent, and so on. And you can obviously do that as well with Claude, and we will come back to that later as well. So each sub-agent has its own context memory, which is very important, because this leaves room for the parent agent to focus on high-level strategy without consuming all of its context capacity, because context rot is a very serious problem. So each one of those agents or sub-agents typically has or is an LLM of its own. So for example, you can use Haiku for one of those, and then you can use Obus for another one, and then use like DeepSeek for a third one, and so on. So due to the inherent looping and communicative nature of LLM programming, state machines emerge as a natural choice for developing agentic LLM applications. For example, if an agent is working on a task and succeeds, it moves to state A. If it fails, it moves to state B, right? Since LangGraph is designed around state machines, it is a perfect tool to program agentic LLM applications. In short, LangGraph coordinates between all those agents, sub-agents. It is an orchestration framework. Okay, so do you have to use LangGraph? No. You can directly use the low-level API like the Claude Messages API if you want, and do your own custom orchestration like Python code or something. You can do that. Later on, we will also talk about the Claude SDK, which is different from the Claude API. So the Claude SDK that we'll talk about later in later recordings is more tailored towards agentic workflows, okay? So LangGraph just makes your life easier, especially for complex state machines. Examples of cases where it shines include, without being limited to, like parallel forks and stateful checkpointing and so on. If you do your own custom orchestration code, you will have to re-implement all of that yourself, but LangGraph actually implements it neatly for you. It does so while still giving you real and proper control, because later on when we talk about the Claude SDK, you actually can do agentic workflows using the Claude SDK, but you lose some of the low-level control that LangGraph gives you, and you will understand this later. So in summary, you can use LangGraph to create non-LLM apps if you want. You can create LLM apps without using LangGraph, and you obviously can use LangGraph to create LLM apps. Okay. Now let's talk about a simple example. So suppose this is the workflow you would like to generate. So you have a start node, and then from the start node you move to node A. Node A is just responsible for printing the count and then incrementing. So you start with the count of 0, for example, then this prints the current count and then does something like count plus plus. And then if count is less than 3, like this here, you actually loop again into node A. If count is bigger than or equal to 3, you just finish and your workflow is done. So you can implement this using multiple frameworks. Here on the left, you see the implementation using LangGraph. I mean, the purpose of this course is not to explain the LangGraph syntax, so I'll just move very quickly here. This is not part of the course, this is not part of the exam as well. But in general, you define some sort of a state that can be a type dictionary or dictionary. Here the state is just like count, which is just an integer, right? And then you define your like workflow here. So you use state graph, and state graph is actually imported from LangGraph. And then you tell it the shape of that state. So this is the state that you would receive and alter, okay? And then you actually add a node called node_a, which is this node a, which is this function right here. So this function receives the state and then again returns the state after some modification. So this function or this node here will just print the state and then return the state object count is equal to state of count plus 1. So this does the increment, okay? And then, so you add this node, and then you add an edge from the start node to node A. So start here is again imported from LangGraph directly. So this is a start node. You add an edge from start to node A, and this add edge means that you always move from start to node A. There is no conditioning. However, from router here, you can either go here or there, which is why you actually use add conditional edges instead of just add edge. So from node A, you actually move on to router, but this router right here, this function right here, can return one of two things. It can either return the string loop or it can return the string finish. And here you are saying, if this returns the string loop, please go back to node A, right? And if it returns the string finish, please go to end. So it's a little bit weird way to write things, but this is how LangGraph works. And here you just do the check. If the count is less than 3, you actually return loop, otherwise you return finish. And then after you create this workflow, you actually need to compile it. This graph flow is a typo, it should be workflow. So this app, you then invoke it and give it the initial state, so count of 0, and then if you run it, you should actually receive those outputs right here. Okay, so this is a very simple example for LangGraph. Now let's talk about LangChain and PydanticAI. So both LangChain and PydanticAI provide an abstraction layer above low-level APIs for different vendors. And this is very like important. Like we talked about using the low level like Anthropic Claude Messages API. However, in my opinion, I think you should for most cases not tie yourself to one specific vendor, because maybe you would like to use Anthropic now, but maybe later you might want to try DeepSeek or like Gemini or something different. So ideally, you shouldn't actually use the low-level messages API except if you know for sure that you are tied 100% to Anthropic. But I mean, I'm recording this course in June and we all noticed how like Anthropic released like the Fable model, and then after this, like just 3 days, they just took it away. So if you are really stuck with Anthropic, you might find some problems like this, right? Okay, so LangChain and PydanticAI actually provide an abstraction layer where you can program to like PydanticAI or to LangChain APIs, and they actually handle calling the low-level APIs from different vendors for you. So changes are minimal in this case. You can just change maybe your API key and the model name, and you are now using a model from a different vendor, which is always nice. So they provide an almost unified interface for all the different APIs in the market. So you can call the Claude API using PydanticAI or LangChain functions or APIs. This removes some flexibility from you. It is not all perfect, because suppose like Anthropic does something extremely like special, extremely nice with a very weird different API, and PydanticAI has not yet upgraded their API to be able to use this new feature, for example, then you lose some flexibility. However, it makes using different models from different vendors seamless. It protects you from being super tied to one vendor. So inside the same LangGraph graph, you can have a node running LangChain code, a node running PydanticAI code, a node running low-level Claude or Gemini API code, and a node running generic Python code like connecting to a database. So this is very important. LangChain does not replace LangGraph, and PydanticAI does not necessarily replace LangGraph, although they are trying to also add a lot of the features that LangGraph has. So I mean, this is a very, very high level view. Okay. So LangChain and PydanticAI are built on different philosophies. Explaining the difference between the two is completely out of scope of this course. This course is about Anthropic or about the Claude API and SDK. Remember, this course is more about the low-level Claude API. Yeah, sure. For the purpose of this course, it is fine to just think of LangChain and PydanticAI as competitors in the same space. Both provide unified interfaces to call different LLM vendor APIs, and both can be used inside a LangGraph node. In reality, obviously, the difference is a bit more complex than just that, but this is an okay-ish enough mental model for this course. So this is a very simple example again using LangGraph and PydanticAI. I will not dive into the details, but I would like you to understand that from PydanticAI, we actually import this agent right here, okay? And then we create two agents. So those are two PydanticAI agents. However, you can see that for this agent, we actually call an Anthropic Claude Opus model. And also here for the critic, you have a Haiku model. Okay. And then you have a graph. So again, this is like LangGraph here. And inside the critic node, you actually call the critic agent, which is a PydanticAI agent. So this is what I just wanted to say here. There is also another very important thing I would like to hint at here, and we will actually spend a lot of our time later on talking about it over and over again because it's very important, which is PydanticAI actually allows you to have a structured output schema. So in general, when you call an LLM, it just like responds to you with some sort of free text. But if you would like to like chain things together, you would like the output of the LLM or the LLM API call. Sometimes you would like it to be structured. For example, you would like the LLM to return a JSON for you or something like that, and the LLM is just like a probabilistic next token generator. So even if you tell it in the prompt, please return a JSON with those keys, it might actually do that, and it also might fail to do that, right? So there is a lot of work about making the LLM actually return the output format that you expect. And PydanticAI actually provides one nice way of doing this, one nice abstraction about doing this, but also the Claude API and the Claude SDK have their own ways of doing this exact same thing. So I am really not tied to Pydantic here, but this idea of a structured output schema is actually extremely important in general. So the way Pydantic does it is you actually import this base model, and then you define a class that represents the output schema. So here the view result inherits from base model, and then you define that the output should have those two like keys, is valid or not, and feedback string. And you see here in the critic call here, or the definition of the critic agent here, you actually define the result type is equal to like review result, which is this one right here. Okay, so now this is very important. Now Pydantic under the hood will actually insert some stuff into the prompt of the model, and then it will actually try to force it to return the output in this specific format. And to be honest, the low-level APIs, for example, the Anthropic low-level API, also allows you somehow, and we will talk about this later, to try to suggest or to force a specific output schema. So PydanticAI will just try to translate whatever you wrote here into the format that Anthropic expects or that Gemini expects, and so on. And then again, we will talk about some engineering like hacks that happen inside the actual Anthropic code. They do this for us to try to force this schema. We'll talk about this later. But from our perspective here, this is one way of trying to force a specific schema. That's one very easy and high level way. So this is extremely, extremely important. Now the initial state is just this dictionary here. Remember here that we define the state as having those four like parameters or four keys. which is the initial state that you use to invoke the app. Okay, this is a LangGraph plus PydanticAI example. So the answer to the question now is obviously A. So a lead AI engineer is trying to architect a multi-agent system for a financial firm. The application must perform initial data extraction, pass the data through a verification loop where the critic agent reviews the coder agent's output, and finally ensure the results are returned as a strictly typed Python object to prevent downstream database errors. The team decides to use a modular stack involving Claude 4.7 Opus model, PydanticAI, and LangGraph. Which component is primarily responsible for managing the state and the iterative critic coder feedback loop? The orchestrator out of those four is LangGraph. See you in the next video. Okay, now for question number 3. A healthcare technology company is building a medical assistant using the low-level Claude API to help doctors quickly extract patients' vitals from the unstructured voice to text transcripts. Okay, the system must send those vitals, specifically heart rate, blood pressure, temperature, to a legacy database that requires a strict JSON format with the specific keys and integer values. During the pilot phase, developers noticed that when they asked Claude to output JSON in the system prompt, the model occasionally included conversational fillers like "here are the vitals I found," or formatted the blood pressure as a string like 120/80 instead of separate integer fields, causing the database script to crash. Which implementation strategy is the most robust architectural choice for ensuring Claude provides the vitals in a reliable, machine-readable format while minimizing the risk of conversational leaks or schema violations? Okay, so as usual, we have 4 options. First one is enhance the system prompt with multiple few short examples showing the exact JSON structure and append JSON only to every user message. B, use the tool's parameter to define a specific JSON schema for the vitals and set the tool choice parameter to type tool name record vitals to force the model to respond via the tool. C, program a secondary validator script in Python that uses regular expressions to strip away any non-JSON text from Claude's raw string response before parsing. And D, switch the model from Claude 3.5 Sonnet to Claude 3 Haiku to reduce the model's verbosity and ensure it stays focused on the numerical data. Okay? So this question is really to introduce the concept of tools or tool use. So what are tools in the world of LLMs? In general, you can think of tools as deterministic functions that do something. We could be reading from a database, writing to a database, doing some complex calculation like solving a differential equation, calculating the area or something like this. You can actually put an LLM inside a tool if you want. For example, you can have an LLM that reads like something or like that analyzes an image. This can be a tool, which is fine, but ideally you should actually, or it is more preferred to make tools deterministic. And this is because this allows you to write unit tests for your tools and test them properly and trust the tools. So now your focus shifts towards making sure that the LLM is calling the correct tool instead of being confused. Is the LLM really calling the correct tool, or is the tool that uses another LLM doing something wrong? If the tool is deterministic, you actually get better sleep at night, okay? But how does an LLM call a function? I mean, remember that the LLM is a probabilistic next token or next word generator. On its own, it can't call functions or APIs. It just like produces text, right? However, you can train it using supervised fine-tuning and using reinforcement learning to actually try to tell the orchestrator code, please call this tool for me. So for example, you can train it to output something like this, like some tags that say like tool, and then call tool name with those parameters or something like this. I mean, this is just an example. So the LLM cannot directly call a tool, but it can actually output a response that asks the orchestrator, please call this tool with those parameters. And then the orchestrator code is just some Python code, for example, or some C++ code or whatever, right? And then this orchestrator code can actually call the tool, right? Can parse this output and decide to call the tool. And we'll see an example for this right now. Okay, so the orchestrator code can be LangGraph or plain Python that calls the LLM, can also parse the LLM output. If it finds those tool tags, it calls the actual tool. Okay, nice. Now, to allow the LLM to say, please call this tool and send the result back to me, you need to give the LLM in the prompt a list of available tools for it, right? The LLM then reasons, like it reads your prompt and then reasons and decides on its own whether it needs to call a tool or just continue its standard next token prediction process without call tooling. Now the Claude API allows you to send a parameter called tools while calling the model. You know, the Claude Messages API, and we will see an example for this. This one expects a list of tools, and each tool is a dictionary with a couple of keys. Typically, you have a name for the tool, you have a description for the tool, which is a reasonable description for the tool such that the LLM can know when to use it. Okay, and then you also have an input schema to the tool, so you are practically telling the LLM, if you call this tool actually is a function that expects those parameters, please give me the parameters to call the tool with. So the input schema defines the input parameters for the tool and the types of those parameters, helps the LLM decide exactly how to structure the parameters to send to the function or to the tool. Okay. So this is an example. So this is a tools list. As you can see, it is a list right here of dictionaries. Although here we actually have only one single tool called calc_rect_area. And this is this one right here. I mean, those names don't need to be the same. Actually, the LLM is not aware of this def right here. It only knows about the string. And then the orchestrator code, as we will see right now, will actually check the LLM output, and if it finds out that the model wants to call this one right here, it will call this one for us, and we will see this. But the important thing is the LLM API call actually needs this tools list. So let's look at this. So you have a name, you have a description, calculates the area of a rectangle, you have an input schema, and then you actually define those like parameters right here. So you have a parameter width, and then you have a parameter height, and you have a description for the width and height, and those two parameters are required. Okay, so this is really the schema of the tools parameter. And then here is how you call it. So you still create your client for Anthropic, and then you use the messages.create, but then you have tools equal tools. So now you are telling the LLM in this specific stateless API call that you have access to those tools if you want. So the LLM is not forced to use the tools, it is allowed to use the tools if it wants. Now, here is what happens for the orchestrator. So the orchestrator can actually check the response. So here you actually return a response, right? The orchestrator can check the response. If the stored reason is tool use, it can actually try to get the width and height from whatever the LLM response had, and then based on W and H, it actually calls this function. So the LLM does not need to know about the actual name of this function. It only knows like this one right here. Okay. Now, to be honest, this code is not super clean, and this is because I didn't actually check for the actual tool name here. I mean, ideally, I need to check the actual tool name, and if the tool name is calc area, then I do this, but then you could have multiple tools. So this is a very simple code, but it gives you an idea of what we would like to do, right? Okay, so obviously this example is simplified. Typically you need to get the tool call out in the orchestrator, feed it back to the LLM as well. I mean, here we just got the result and that's it. But typically you actually get the tool output or the function output, feed it back to the LLM, and then the LLM will continue reasoning and might require another tool call, and then you might return back to the LLM and so on. Here we just got that result and just printed it, and that's it, right? You can also implement a simple while true loop for a simple chat agent if that's your application. When things get really complex, you should probably consider using LangGraph. So I mean, this example did not use LangGraph or didn't even use PydanticAI. It's just a linear orchestration code. If things become more complex, you should consider using like LangGraph, for example. Okay. So here, this is another example. So again, we actually still pass in the tools here, but then I think this code is a little bit cleaner. For example, because I try to check here if block.name is equal to calc rect area, then do something. Otherwise, I just say unknown tool. So it's a little bit cleaner with some extra guards. And then I actually get that result that we calculated right here and create a message and append it to the list of messages. And this list of messages I will send back again to the LLM. So that the LLM actually in this case will have the entire history. And this is actually important. I mean, remember here that we had one message, right? So this is the first message, like the room is 10 by 12, what is the area? And then the LLM actually responded with a message asking for a tool use, right? Or a tool call. And this message also got appended to the messages list. So this is a second one. And then we actually call that tool or that function. We create another message and we append it as well. So we have 3 messages, and then we send those 3 messages to the LLM, and then the LLM actually will now out the final answer for us. So I mean, this is kind of a workflow, although it's a very simple workflow, again, not using LangGraph or anything. Okay. So while the CCA-F exam typically won't ask about PydanticAI, it is actually worth noting how using a higher level API simplifies things compared to the Claude Messages API. Okay, so let's talk a little bit about how we can do something similar using the PydanticAI API. So the PydanticAI API handles a lot of the back and forth for us automatically. It also handles the tool schema creation in a way that the Claude API expects. So this is the same example roughly using PydanticAI. So in Pydantic, you import the agent, and then you create an agent, and then system prompt, you are a helpful math assistant, use tools for calculations. Okay, now the way you define tools if you use Pydantic is by this decorator. So you define an agent called like agent, and then you can do add agent to the tool. So this is your way of telling Pydantic this is a tool, and you have those parameters, and you have this context which is of type run context. We'll talk about it in a minute, but the important thing here is the width and height. And then you need to write this docstring here, calculate the area of a rectangle, and then the arguments. So I mean, this is also important for Pydantic. You need to write those docstrings in order to tell the LLM some context or some information about this tool, okay? And then this is really just it. Like, I mean, you run the agent using agent.run sync here. So you send in the prompt, the room is 10 by 12, what is the area? And then you actually get the final result. So Pydantic abstracts a lot of those internal loops for you. So you do just this and all of this happens. So you send the initial prompt, and then you receive the tool use with stop reason tool use. So this happens internally inside Pydantic. And then Pydantic also executes the actual tool, sends the result back to the LLM, and then returns the final result to you. I mean, compare this one. This is one line right here. Compare it to all what we did here, where we try to append the messages manually ourselves, and then we actually call the tool ourselves and so on, right? So this is a lot of work. Using PydanticAI, you abstract a lot of that and makes your life a little bit easier at the expense of losing some control. Now, PydanticAI under the hood still calls the Claude API, right? So it really gets what you wrote here and still creates something like this, like this right here, because this is what the Claude API expects at the end of the day. So it converts what you wrote into this format for Claude, and maybe if another vendor like Google or something expects a slightly different schema, a slightly different format, it actually formats the same input into a different format, right? So using Pydantic, you always write things in this way, and then PydanticAI is responsible for translating it into the slightly different formats for different vendors. So again, this is really not part of the exam, but it is nice to know about, I would say. Okay, so in PydanticAI, you define a tool function by using the agent.toolDecorator or @agent.toolDecorator. In addition to the typical tool parameters that the LLM outputs, you can have an additional context parameter of type brand context. You can use this for sending parameters that you don't want the LLM to guess or even see. So this is extremely important actually. I mean, right here, the width and height parameters are actually outputs from the LLM, right? The LLM, again, only knows about its context. So for example, you might have some secrets you don't want the LLM to know. For example, you could have some, personal identifiable information, some email addresses, some phone numbers. You would like to use those, but you don't want the Claude API to know about them, because when you call the Claude API, you're actually sending all those parameters into the cloud or to Anthropic, right? Maybe you don't want Anthropic to know those things, even if they actually implement some security measures and so on. So using Pydantic, you can actually pass in some, inputs that are not output from the LLM. Because if the LLM outputs an email address, it needs to be made aware of it, so it needs to process it, and then it can actually output it correctly. However, you can actually bypass the LLM entirely for some of those parameters, sometimes because of security reasons or privacy reasons, but also sometimes because you have some deterministic things, right? For example, the interest rate, for example, and then you don't want the LLM to hallucinate some sort of a different interest rate. You want to be 100% sure that the correct interest rate is being used. So this is one way of doing this, right? Here you pass in some parameters, right? Okay, so for example, current interest rate or user's email address. Remember, when you call the LLM API, you are sending your sensitive data to the LLM, right? If you don't want this extra parameter, you can use a plain tool decorator instead of tool. Our simple calc area use case doesn't really need a context object. I just put it here for completeness. Okay. Now, in addition to the tools parameter, you also have a tool underscore choice parameter. And this one is very, very, very important, because if you just pass in tools, you are telling the LLM you can use those tools, but you can also not use them. I mean, it depends on your own reasoning. However, using a tool choice, you can actually force the LLM to use one specific tool, or to use at least one of the tools, or you can leave the default behavior. So for example here, if you put in tool choice is equal to this, so type is equal to tool and name is calcorrect area, then you actually force the LLM, it must use this tool. It must use this tool. But if you leave it, then it's up to the LLM to decide, okay? So you actually have three options. Auto, this is the default, the model decides. Or any, this forces the LLM to use any tool, but it must use a tool. It can't just output, something without using a tool at all. So it must output a tool use block, or a tool use response, or a tool use request. And you can also use tool. This forces the LLM to use one specific tool. So in summary, those are your options. You can have type auto, or type any, or type tool, and then give a name of that tool. This is allowed by the Anthropic Claude Messages API. Okay, so if you want to guarantee that the LLM output follows a specific deterministic format, forcing tool use is one of the most robust ideas. But how? How does this happen? I mean, isn't the LLM still probabilistic? Yes, the LLM is probabilistic. However, when you call this API, you don't just call the LLM directly. I mean, Anthropic does a lot of engineering behind the scene, and it can actually do some nice tricks in order to force an output that you expect For example, yes, the LLM is a probabilistic next token generator. However, at every token generated, you can actually have a look at the entire probabilities across all the vocabulary. And if you want JSON, you can actually artificially increase the probability of tokens that represent a valid JSON format. For example, like the curly braces, and then maybe a string for the key, and then a colon, and so on. So you can do some engineering to artificially increase the probabilities of some of the valid tokens and zero out the probabilities of completely invalid tokens. Similarly, if you expect some response that starts with like tool in some tags, you can also increase the probability of this specific format using some engineering hacks. This is called guided decoding. So this is really what happens when you call this create with a tool choice of type tool, for example. You can force that. So this is what I wrote here, yes, but the Claude API does some deterministic logic to force the LLM to respond in a desired format. For example, while the LLM outputs probabilities for all possible tokens in each word generation step, the API's internal code can boost the probabilities of tokens that make a valid JSON structure or that start with tool use word and zero out the probabilities of tokens that break the JSON structure. It is important to note that even if the structure is correct, the actual values can still be wrong, can still be hallucinated, right? So you need to add more validators in your orchestrator code. For example, you can make it clear in the prompt that the LLM that the only allowed values of a string parameters are orange or blue, but the LLM can still say red, right? This is why PydanticAI gives you a validation decorator as well to check not just the schema, but the actual values as well. So the validator runs before the tool call. If the inputs are wrong, it can reprompt the LLM to retry again. So note that this is actually different from the schema validation. So the schema validation is one thing, but confirming the actual values are within the allowed values is another thing. So this is an example as well. So you have a tool here called setUIColor, and this is Pydantic again. However, you have a validator for this tool. So you have agent.validator for setUIColor, and this receives the parameters before the tool is called, and then the allowed is orange and blue. And if whatever you received is not in allowed, you can raise a model retry, and then Pydantic will actually retry calling that model, and it will send the model a message saying forbidden use only those, for example. Okay, so again, this is another validation. Again, this is not part of the exam actually at all, but it's important to at least have some mental model of this one. Okay, so what is the answer to the question? So the question says, which implementation strategy is the most robust architecture choice for ensuring Claude provides the vitals in a reliable, machine-readable format while minimizing the risk of conversational leaks and schema violations? The answer is B. You can use the tool's parameter to define a specific JSON schema for the vitals and set the tool choice parameter to type tool, namely record vitals. This actually forces two things. It forces the LLM to call the record vitals, or at least to request calling the record vitals with the correct parameters, and this is really what you want. But now let's actually think. Why is option A incorrect? The option A says enhance the system prompt with multiple few short examples showing the exact JSON structure and append JSON only to every user message. This is not super bad, but it's also not super reliable. No matter how you perfect the system prompt and the user prompt, the LLM is still probabilistic next token predictor. Yes, this will definitely help, but it is not a guarantee, and sometimes you actually need a 100% guarantee. Okay, why is option C incorrect? So option C says program a secondary validator script in Python that uses regular expressions to strip away any non-JSON text from the Claude's raw string response before parsing. This is a step that runs after the LLM is done. It wouldn't help the LLM itself. The good thing about the tools parameter and the tool choice parameter is actually it controls how Claude gives the response to you, which is nice. But this validator, yes, you can have validator with retries. This is actually nice. It's not bad. Again, it's not bad, but if you use the tool choice parameter, you actually affect the decoding process itself using guided decoding. Okay, that's it for this video. See you in the next lecture. Okay, now with question number 4. So an AI architect is designing a system that requires an LLM to interact with two different components. Component A is a proprietary session logger function that resides within the local application code and accesses temporary variables stored in the active script's memory. Component B is a centralized company knowledge base containing real-time product documentation that must be accessible by multiple independent AI applications across different departments like HR, engineering, and sales. Which architectural approach best aligns with industry standards for reusability and interoperability? So you have 4 answers as usual. The first one is implement both components as local tool definitions within the individual application scripts to minimize network latency. Option B is implement component A as a local tool definition and component B as an MCB server. Option C, implement component A as an MCB server and component B as a local tool definition to ensure the model has direct access to the local memory. Finally, option D, use system prompts to describe the logic of both components as the LLM can simulate the tool outputs without a protocol. Okay, so this question is meant to introduce MCP, Model Context Protocol. So in a previous question, we dived into tool calling. We created our own tools and functions locally, like this calculate area function that we created locally, and we made sure to pass in the correct tool schema to the Claude API call. But what if we want to use an external third-party tool? For example, a tool created to interact with Google Drive, for example, that maybe Google maintains or a third-party like creator maintains. What if multiple teams want to use the same set of tools? I mean, imagine a huge company and then you have like 10 different teams and all need the same tool in different applications. You wouldn't really want every one of those teams in every one of those applications to recreate the function, to rewrite the function again, right? You would like some sort of centralization because this is better for debugging, this is better for maintainability and so on, right? What if we have a dedicated team working on creating a tool hub or a tool registry that dynamically expands very often, and we would like to give our LLMs the ability to discover the new tools automatically without changing our code? This is actually very important. I mean, what we did in the previous lecture, or in a previous lecture, we defined the list of tools and gave it to the LLM in the prompt, right? But this is a static definition of tools. What if we would like the LLM to auto-discover tools? This is something that is very important. What if a subject matter expert decides that the best way to steer the model towards using the correct tool out of the registry is via a specific prompt template with specific details? This is an important thing. We'll talk about this in this lecture. What if our LLM needs to know about different resources in a company? It can create good information to use within the tools. For example, you would like to have access to like the documentation of all the ongoing projects so far with different clients or something, and you'd like your LLM to be able to query those like documents, right? Again, from a central place. So all of this is to introduce MCP in a way. So enters MCP. MCP is an LLM first standard protocol. It is considered the USB-C for AI. Developers can define multiple MCP servers, and each server exposes a set of tools or functions that specialize in one domain. So for example, you can have an MCP server for math. This one could expose some functions / tools to solve like linear equations, differential equations, integrals, and so on. And it could be hosted somewhere on the cloud or locally, but it is a server that is specialized for math and exposes multiple tools or functions that solve some mathematical problems. You could have another separate MCP server that exposes tools or functions to talk to an SQLite database, or an MCP server that exposes functions that can do web search, or even do some like file system operations like deleting files, modifying files, searching files, and so on. We will see how to create a custom MCP server later. Okay, but this is the idea. You have this concept of an MCP server, and whenever you have a server you also have a client, but the client will be your own code, your own orchestration code, or like for example your LangGraph or something like that. So an agentic AI developer can use any of those MCP servers for their LLM application in a standardized way. And this is the important thing about MCP. It is a standard that you can use with multiple different vendors as well. So they don't need to be the one creating the tools. The same way you don't need to invent an external keyboard interface yourself in order to use it. You trust that the whatever keyboard supports the USB-C interface and you can easily use it within your laptop. So the LLM itself, this is very important, the LLM itself does not speak to the server. The orchestrator code does the communication. So this is very similar to when I said that the LLM itself does not call the tool. It just requests some tool call, and then the orchestrator is the one actually calling the tool. Okay, so a simplified way to use an MCP server in an LLM application would be as follows. So your LLM orchestrator acts as an MCP host or client. I mean, typically you use the word host and client a little bit interchangeably, although they are a little bit different, but in this context they can be thought of to be the same. Or like more accurately, the host has a component that acts as a client. The client actually is responsible for maintaining the connection to the server. Okay. So the server, or the host, maintains a persistent connection using HTTP or STDIO to the MCP server via an MCP connection client. So STDIO is standard input output. HTTP is the one for the web, right? So you can think of the MCP client as a piece of code inside the MCP host that is responsible for maintaining the connection to the server. So you have a discovery phase where the host sends a standardized JSON RBC request to the server called like tools list. So we will see a concrete example for this, so don't worry, but really the host or your orchestrator code will start by trying to ask the server, please tell me the tools that you have, please list the tools or functions that you have. So it sends a request using JSON RPC. RPC stands for Remote Procedure Call. And then the MCP server responds with a list of tools in another like JSON format. So it responds with a list of tool definitions. Each definition follows the model agnostic MCP schema, which includes the name of the tool, a description of the tool and when to use it, and an input schema for the tool, like the parameters of the functions. And you actually could realize that this is very, very similar to the standard format for the Claude API, how you define tools for the Claude API. It's actually very, very similar. Okay, so this is an example of a JSON RPC request sent to discover available tools. So for example, the host or the client can send this one to the server. So JSON RPC 2.0 and then some ID, and then the method, this is really what you want, is I would like to list the tools and no parameters. And then the server can respond with something like this. So for this ID, so ID 1, this is a response for this request, and this is the result, and those are the tools that I have. Here it only has one tool that's called calculate tax. You have a description for this tool, and then you have the inputs to this tool, amount and region, and both are required, right? Okay, so let's talk about why allowing HTTP and STDIO. So again, those servers can be hosted remotely. For example, you can call an MCP server that is hosted by Google or something, but you can also have them locally because some MCP servers actually expose tools to like handle the like local file system, for example, right? So you can communicate with MCP servers using HTTP or STDIO. STDIO is typically for local MCP servers and HTTP for like remote servers. However, also for local servers, you can use HTTP if you want, although STDIO is like more like common in this case. So some MCP servers can reside locally on your machine. Think of a server exposing tools that can edit your local file system for coding. For those servers, you need to send the JSON RPC request locally. No internet involved in that communication to the server. However, if the server exposes a tool and this tool needs to use the internet to query something, this is obviously allowed, right? So in this case, your MCP host, your orchestrator code itself, spawns the MCP server as a separate local process and communicates with it using std in and std out. Note that a tool inside the server can still access the internet, okay? On the other hand, some MCP servers can be hosted remotely. Think of an MCP server maintained by Google to organize connection to Google Drive or YouTube. For those servers, you send the same JSON RPC message over the internet. Technically, you can also have HTTP locally or use HTTP locally to connect to local host for like the local MCP servers, but STDIO is generally preferred. Okay. Another point to pay attention to is the following. A local MCP server is just yours. If your MCP host or application actually ends execution or crashes for whatever reason, the MCP server process needs to end as well, or actually will crash as well. A web accessible MCP server, on the other hand, can typically handle lots of requests from very different people, very different applications. It is typically always available. So it can be actually a standalone server that's always running, but it can also be a serverless like function on a cloud service that gets woken up when a request hits, but it needs to be available. So think of a weather API service that answers to MCP requests across the globe, or a Google Drive MCP server, and so on. Okay, but how do I call a tool? So using the same RPC protocol, you can also request the server to call a tool for you. So since the LLM now has access to all the tools, it can output a standard tool call block, and then the orchestrator might read the response of the LLM and then realizes that the LLM needs to call a tool, and then it can send an RPC request to the MCP server again. So something like this. Like, note that the method here, it's called tools call. Previously it was called tools/list, right? So here tools/call, and then you actually send in the actual tool that you would like to call and the arguments of this edit file tool, like a path and content, right? So the server can then execute the tool call and then returns a response depending on what the tool returns, right? So for example, again, here the ID is tool call 3, and then this is the response for the same request, tool call 3, and then this is the result like that the tool actually returns, and then you consume this in the orchestrator. You can send it back to the LLM to continue reasoning. So in addition to exposing tools, MCP servers also expose resources and prompts, and we can talk about this. So we have seen how an RPC request can ask for a list of available tools. Similarly, we can ask for a list of available resources and a list of available prompts. But what are MCP resources and MCP prompts? Okay, so let's talk about resources. So you can think of MCP resources as read-only data that the MCP server can provide to you. So resources can be database entries like file contents or similar entities. Like they can be something that is read-only. For example, you can think of a company creating an internal MCP server that exposes maintained documents for all the projects currently in progress for all the customers. Technically, you can still use a tool call to read the data from the server. Obviously, I mean, a tool call can really do anything, right? Because you can call a tool that acts as like read from database or read the documentation. However, generally think of a tool as a request to do action, while a resource is a request to read some data. So I mean, it's a little bit of a cleanup if you would like. Okay, the tool is very generic. You can do anything with the tool, but if you know that you just would like to read some resource, some documentation, some policy, then you can use a resource. MCP servers are allowed to expose to you lists of tools, lists of resources, and lists of prompts, and we'll talk about prompts in a second. But before that, you can actually send a JSON RBC request again, and the method can be resources/list. So please give me all the resources that you have, and then the response can be a list of resources. Again, here we have only one resource that is like called Ahmed Fathi super important materials, and this is the URI, and this is description for that resource. And then if you would like to read that resource, you need another request or another RBC request, like with a method that is resources read, and then give it the exact URI and as a parameter, and then it can respond to you with the contents of that resource. For example, this was a text resource, so it responds to you with some text. Okay, now prompts. Prompts are actually very interesting. I mean, typically you think of prompts as something you write in your application. However, again, prompt engineering is important, and sometimes maybe a couple of subject matter experts actually sat down together and designed the perfect prompt for something, right? And then you don't want to rewrite that prompt and do the prompt iteration and the prompt optimization yourself, because sometimes for like hard problems, prompt optimization can actually take some serious time. So some persons or some centralized like department can do this. And then you just ask the server, please give me the prompt to do XYZ, for example, to do proper code review. And you'll see an example here. So let's read up first. So similar to tools and resources, there are defined method strings that you can use to list all prompts that the MCP server exposes, or to get a specific prompt in the JSON RPC. But why would we want that? Like MCP prompts move the instruction logic from the host to the server. This allows for a higher degree of standardization. Again, you could have like multiple AI applications and all could make use of the same prompt, so why not? This also allows for a cleaner host code, not cluttered by a tremendous amount of different system prompts for different agent nodes. Because imagine you have a large graph with a lot of agents and every one of them needs their own prompt. You would have to define like different prompts for every like different node. And again, if you have multiple AI applications, you will repeat this all over again. So this centralization actually leads to cleaner host code. In addition, it allows for parameterized expert-written prompts to be reusable without having to reinvent the wheel. Okay, so for example, an easy to remember example would be a code review prompt. So when you review code or create an agent to review a code, you need to keep attention to multiple angles at once. For example, you need to keep attention to clear comments, function and class naming conventions, logical errors, syntax errors, unit tests, type hints, internal coding guidelines, for example, the parameter orders for the functions, and so on. So an MCP server can provide you with a tailored parameterized prompt that you can use with your LLM that already lists all the edge cases the LLM needs to consider, and you can spend a lot of time working on this one time and then keep using it in all of your applications. The orchestrator can get this prompt, inject parameters, and passes the prompt to the LLM, and the parameters could be a specific file or a specific repo and so on. Okay, so this is a very simple example about using an MCP server with the Claude API. So think of this as some sort of pseudocode that summarizes how to use MCP tools in an orchestrator app that uses the Claude API. This snippet uses the low-level requests library, this is a Python library, to show some internal details. So here we use requests to actually communicate with the MCP server using HTTP. In practice, there are other packages like the MCP package, and we will handle this in a later video or a later question. But for now, for this very simple example, you import requests and Anthropic, and then you have some server like mathmcpserver.com/RPC. You create your client, right? But then this is a function that you run at the beginning of your application. This is where dynamic discovery happens. So get the tools directly from the server. So you create a JSON RPC payload with tools/list. and then you actually post to this URL, MCB URL, this payload, and then you get the response here, and then actually return the response like as a list in a way that Anthropic like Claude API or Claude Messages API expects. So remember, this would be like our tools parameter. So those are the available tools. You call this function, and again, this is dynamic. You can like just shut off this application and then run it again, and if the server changed or exposed more tools, you'll have the new tools, which is pretty nice. So now at some point, if the LLM actually wants to call a specific tool, then again you create another JSON RBC like object right here with tools/call, and then you actually send the parameters based on what the LLM actually thought the best parameters should be, right? And then this is it really. You actually send this again using the requests library to the same URL, okay? So typically you wouldn't use the low-level request API and you wouldn't create the RBC JSON manually. Instead, you can use pip or UV to install the MCB package and use it. It handles some boilerplate for you, and we'll show an example for that in a later lecture. We also didn't cover how we can create our own MCB servers in this lecture using the fast MCB package. We will also cover that in a later lecture. But now let's try to answer the question, and I guess after all this explanation, the question is very easy to answer. So the question asks, which architectural approach best aligns with industry standards for reusability and interoperability? So remember again, component A actually is session logger function that resides within the local application code and accesses temporary variables stored in the ActiveScript's memory. So since this one is actually local and it needs to access some like memory variables in the current script, it shouldn't be an MCB server. It should be like some local function similar to what we did in a previous like video. However, component B is a centralized company knowledge base containing real-time product documentation that is used by different departments, and this screams MCB, and this is why the answer is B. So implement component A as a local tool definition and component B as an MCB server. This is the answer to this question, and see you in the next lecture. Okay, now for question number 5. You are building an AI-driven maintenance assistant for a factory. The assistant needs to access a vibration sensor connected to a local PLC. The sensor data is accessed via a proprietary Python library that only runs on the factory's local Linux server. The Python library continuously saves the vibration frequency to a local database. To identify a failure based on the maintenance engineer's request to investigate, Claude must calculate the average frequency over each 60-second interval in the incident investigation window. Okay, then take the maximum of each of those like averaged values and compare it against a baseline safety threshold. Which of the following architectural implementations is best to provide this data? So you have 4 options as usual. A, create a custom MCB server that exposes the database table as a resource. Provide Claude with a system prompt so it can fetch the rows and perform the calculation. 2, develop a custom MCB server with a tool called Analyze Vibration Incident. This tool executes the averaging and comparison logic and returns a concise summary to Claude. C, map the baseline safety threshold as a resource and the raw database as a resource as well. Use an orchestrator to inject both into the system prompt at the start of every session to ensure Claude has the full context for any potential investigation. Finally, store the vibration frequency logs in a vector database. Use a standard RAG pipeline to fetch the most relevant frequency snippets when the engineer asks to investigate an incident. Okay, so I mean, this question is really about introducing custom MCB like servers, And I think I can just answer the question now and then introduce how we create a custom MCP server. I think the solution to this one is actually clear. It should be option B. Why? Because we are performing an action on some database entries. I mean, we talked about resources versus tools before, and in general we could say that you create a tool if you would like to perform an actual action, and in this case the action is some transformation of the data of the database. So you actually retrieve the data, you run this averaging process over like windows, and then take a maximum and compare to a baseline. So all of those are actions. You are not just reading database entries, right? So this is why you actually use tools and not resources. So this actually clarifies between A and B. Like C is not very good because in this case you actually get everything into Claude, and then you expect Claude to be able to do those calculations itself. Like the actual LLM can't really do calculations, right? I mean, the LLM is just a probabilistic next token generator. So even if you pass to it all the database and some rules, it can hallucinate the values. To do proper and deterministic calculations, you actually need to use functions or tools, okay? RAG is completely irrelevant in this case, so that's not an option. So here the answer is question B, create an MCP server with a tool. Why a tool, not a resource, even though we read from a database? Because a rule of thumb is if you want to do some logic or calculation on the data, use a tool, not a resource. Resource should be for almost static or read-only content. Okay, but the important thing about this question is I'd like to introduce how you might create a custom MCP server. Okay, so this is one way of doing it in Python. So there is a package called fastmcp. You can install it with pip or uv, and really roughly this is some code to do it. So you define some MCP and this equal to fastmcp and give it some name, and then using this variable name you can actually define tools using those decorators. So for example, at our super mcp.tool, so here you define a tool called add numbers, and then you define the description or the doc string of the tool, and this is a tool. You also define another tool called get server name. In the same way you can define a resource in this manner, and you can also define a custom prompt, right? So this is a prompt that is parameterized. So this generates a structured prompt for code review, and then this is actually the actual prompt, and you can inject the actual code to review. So all of that we talked about before, we just didn't cover how to define a custom MCP server, and this is it. And then you have like this main. So now you define the server. How do you use this server inside your orchestrator application, like a LangGraph application or a Claude-based application and so on? This is what we will cover for the next of this lecture, and it will actually involve some not super easy Python constructs, so we will explain those as well. Okay, so now you can deploy this to a server with an endpoint to communicate with it using HTTP or using stdio. So the following code, it doesn't look very easy, but we will actually analyze it. The following code is how you would actually use your custom MCP server. So let's go through it very quickly, and then we'll explain a lot of the concepts. But I would like you on a very high level to understand that you actually define the server path, and the server path is just a Python script at this point, right? Super powerful math mcp.py. And to run this server, you just run python 3 super powerful math mcp.py or something like this, right? So this is what you define here in this stdio server parameters. So sys.executable, you can think of this as this is just Python 3 or Python. And then args is a string of server path. So you actually use this one, and this one, for this one actually you use the MCP package. So there is a package called MCP that gives you client session, stdio server parameters, and also, you know, stdio client. We will walk through this a little bit more in detail later on. But what I would like you to understand on a high level is you actually get those like server parameters, which is this like command really, and you pass it into stdio client. And this one will return to you two objects responsible for writing to and reading from the standard input output. So using those two objects, read and write, you can write to and read from stdio, which is the way to communicate. In this example, you are communicating using stdio, not HTTP. Okay, so you get those two objects and actually pass them to client session, which is also given to you by MCP. And this session right here actually exposes some useful functions like initialize, which initializes the communication between your script here, your client, and the server. And also it has some like functions to call a specific tool with a specific number and with specific arguments. And under the hood, this one is responsible for creating the JSON RBC like string or object that we talked about in the previous video, right? So it's kind of an abstraction layer in order for you to not be needing to write the JSON RPC yourself. So you have like some functions like call tool, and read resource, and so on. And then in order to run this, you actually use asyncio.run run orchestrator, which is this function right here, and we will talk about Asyncio. So I mean, a lot of the things we will cover in this lecture is about Asyncio and also about this kind of like what is this with, what does it mean, what is this read and write, and so on. So we will try to explain this code. If you are familiar with Python, you should actually be aware of this already, right? But if your Python is not that strong, I'll try to cover the details a little bit more. But to be honest, to be absolutely honest, the Claude Certified Architect exam will not ask you about syntax. So think of this as some extra knowledge. If you are just satisfied with the answer that I gave in the second slide, you can move on. However, I think to build real applications, you should at least be somewhat familiar with Asyncio and Async with and Async def and so on, which is what I will cover. And also we'll need that again in one of the next lectures. Okay, so wait, what if I have no idea about Asyncio? I don't know what Async with means and I can't understand this code at all. So let me give you a super quick refresher on Python context managers and on Asyncio. So this again is not part of the exam, but you should know about it. So there is a with keyword and an async keyword, and those actually represent two different like Python concepts or constructs. So you can have in some code base, you can use async without with, you can use with without async, and you can use async with together. So let's actually cover everyone separately. So let's talk about Python context managers. We are now covering the with part of the equation. So in Python, you can define classes that follow the context manager protocol. So this is some sort of class called managed resource. And note, you actually define two functions, one called underscore enter underscore, and then the other one is underscore exit underscore. And this one must actually take some extra like parameters here. So what is this? I mean, if you define a class in this way, you can use it with the with keyword. And there is a nice thing that happens is once you go like out of that block, the exit function gets executed automatically. So actually, if you define a class in this way and use it with the with keyword, then enter gets executed automatically on enter, and then exit gets executed automatically on exit, which actually gives you some sort of proper resource management or automatic resource management. So if you do that, you are allowed to use that class with the with clause. When you go out of scope, not score, this should be scope, of the with clause, the exit function gets automatically called. This is why the context manager protocol is used for resource management. For example, you need to make sure that a connection to a database is closed, for example, automatically after you are done interacting with it, or a connection to a file or something, or you just would like to let a server know that you are done for the day. So again, on exit here, you can really write whatever you want. So maybe you close a connection to a server, close a connection to a database, like release some handle of a specific file or something like this, right? So this is just Python. This is not really too much tied with Claude in any ways. It's just pure Python. So if you'd like to use this, you actually use it in this way. So here you kind of instantiate an instance of this class, and then so with managed resource as res, print res, and note that the variable res will contain whatever is returned by the enter function, not the constructor, not the init function, just the enter function. So let's actually run this code and see what will happen. So this is the full code, and if you print res, you actually see this is the output. So you get, hey, I am a managed resource, which is exactly what you return from enter here, okay? And then you actually see no errors found, and this is because here on exit, this automatically got executed, and there was no error found, so error class was actually none. So we went into this part and we printed no errors found. So this roughly on a very high level covers this like Python context manager idea. But now what about Async.io? So on a very high level, Async.io is a Python library that allows you to run concurrent tasks or jobs on a single thread. So it stands for asynchronous I/O, obviously. So it allows you to create a manager or an event loop for the tasks. So this one manages those tasks. The manager can start a task, suspend a task, start another task, suspend it, and then resume the first task, and so on. So the manager typically has like internal queues for those jobs or those tasks. So it has queues for ready tasks, suspended tasks, and so on. So this is especially useful if some tasks spend a lot of their time waiting for something else. For example, you send a request to a server and wait for a response, which happens a lot with LLMs, right? Or you actually would like to send a request to an I/O device like a hard disk, and then again you're waiting for a response. So in general, you don't need to keep the CPU busy while just waiting for the server or I/O to respond. So you actually would like to release the execution or like yield the execution, and then another process can run for a while until the I/O operation or the network operation is done and signaled by the operating system. Okay. So we will dive into this again actually in more detail in a later lecture when we cover like Python generators and asynchronous generators. So don't worry if things are not fully clear now. However, it should be clear enough in this lecture as well. So on a very high level, if you write something like await some function call, which is similar to what we like wrote here, you have await and then some function call, await session.initialize or await session.call tool. So let's understand what happens when you write something like this. So if you write something like await some function call, the code inside some function call starts executing, and it has a mechanism to yield the control back to the manager or event loop object when it reaches an I/O or network operation. So we will cover yields again later when we cover generators, but you can think of it as this function actually has a lot of code and it can call other functions and so on. But at some point you actually might see some sort of a yield statement similar to return. So yield statement just says, you know what, just release now the control to the event manager because I'm going to do something that might take some time. For example, it can be used in other like situations as well, but this is how you could mentally think of it in this context. So when the manager object gets notified about this yield, it can then run one of the other concurrent tasks that are scheduled until that second one itself possibly either yields or finishes. When the first function gets ready to resume, like the I/O operation is done, the manager object can resume it again because it gets moved into the ready queue again. So roughly this is what happens. So the funny thing is, I mean, the code I shared earlier doesn't really do any background execution, and we will cover how to do some background execution. So why do we use async and await in this code even though it doesn't really do any background execution? How do we even create and schedule those background tasks? I just would like you to understand here that if you have await like this, so await session initialize actually does two things. It does what I described, where it can, I mean, if this function has like a yield inside of it, it can stop executing and release to the manager or to the event loop. However, the event loop will not just continue executing this thread right here, because this thread actually is sequential. It depends on each other. So those are not like running in parallel or anything. It can execute another concurrent task. But here, we did not define any other concurrent task. So in this code snippet, we are still sequential. And we are not really making use of the async IO, because here we are awaiting. So yes, we released control, but then there is no other background task. So we are waiting anyway. The reason why we still do this is because the MCB package actually is built upon async IO, and we kind of have to use this pattern if we would like to use this MCB package. And it is built upon async IO because in general, in like larger like agentic applications, you would need some concurrent tasks. So I mean, this example is just too simple to show the power of async IO in this case. Okay. So note that in this example, you have multiple await function calls after each other. However, there are no background tasks to run while waiting. Contrast that with the following example, where we do have a simple background task created using the create task function. So async IO has another function called create task, and this is one way you can use to create those concurrent background tasks. So actually, this is another function called heartbeat. So async def heartbeat. And this just have a while true, so it runs forever, and then it prints something, and then it does await async IO.sleep. And again, this sleep right here actually could have an internal like yield, so it can yield back to the event manager. The important thing here is this function right here, you put it inside this line. So background task is equal to async IO.create task heartbeat. So now you have actually two different jobs in the queue of async IO in this case, and whenever one of them yields, the other one gets resumed, if it can be resumed right now, if it did whatever it was supposed to do, right? So you have two tasks. So you first create this task. So this one does not run the function, it just puts it on the queue of ready tasks, okay? And then you actually have await session call add numbers, and this one actually has a server call, so it might yield at some point. And when this one yields, the background task actually gets executed or starts executed, and then it goes here, and then it can have another yield. So when this one actually yields, then the orchestrator or this event loop can resume this one if it is now on the ready queue. So for example, calling tool, you send something to the server, and while you wait, this one runs, and then when this one yields again, maybe this one is done and you received the response, so actually continue execution and then move here to background task.cancel and then final result. So this gives you some sort of responsiveness in order for the user to not be annoyed that they are spending a lot of time waiting for adding two numbers, for example. Okay. So this is roughly one way where you can create two different jobs. We'll talk about this later as well. So why did we use await async in the original example? It is because the MCB package is built on top of async IO, so you are kind of obligated to use the await async pattern, even if you technically don't need that concurrency for this specific very simple example. So we talked about await, but we didn't talk about async itself. I mean, here you have async def heartbeat. So what is that exactly? So when you define a function using async def and then call this function, the function does not really execute directly. Instead, this function or this call returns a coroutine object. So you can think of a coroutine object as a job or task that can be scheduled later. Like this is some sort of a wrapper around a function. So for example, if you have async def some function and then do something like x equals some function, so it feels like you are calling the function. However, this will not really execute the function. It will just return an object, and this x will be assigned to this object, and this object is a coroutine object. So you can think of it as a packaging for the function, and then this packaging gets put onto like the queue, and then it can be executed later by this event loop or orchestrator. So x is a coroutine object, no execution yet. So now you can do something like await x. right? Await X or await some function directly if you want, and this actually starts execution. So the code gets executed sequentially in this case. The next line in the code is never executed until this function is done. However, another concurrent task can be executed if X yields. So I mentioned this before, let me iterate again. So if you do await session to initialize, this create task will never get executed until this one is done, not until it yields, until it is completely done. So if you yield, if this one kind of yields, you still wait here because there are no background tasks yet. But then you create this background task, and then if this one, like session.callTool, if this one yields, then this heartbeat can actually execute because it is already another task. However, you can't move past this line except if this call tool is completely done, not just yields, okay? I hope this is clear. You can also do something if you do asyncio.create task, so the code gets scheduled to be executed. It gets added to the ready queue of the event loop. However, it does not start execution until another process yields. So I mentioned this as well. So now back to our original script. This is the original script. Note how we call asyncio.run orchestrator. This is what creates the main event loop or task manager. So this line right here towards the bottom, this is the one that actually creates this event loop for us. Okay. Sys.executable just translate to Python or Python 3. So we are literally just telling the script that to run the MCP server, use Python, super powerful math MCP.py. So here I'm referring to this here server params here, which get passed into the stdio client. Okay. So async with, I mean, we covered with, we didn't cover async with, but it is really very, very similar. So it's really similar to just using with, but it is the asynchronous version of it. The class implemented the two functions, aEnter, which is asynchronous enter, and aExit. So I mean, it's similar to enter and exit, but for the asynchronous like version of it, instead of enter and exit, but the idea is roughly the same. So the aEnter function returns the read and write objects that can be used to read and write to stdio. So this is why here you actually get as read and write, because the enter function or the aEnter function returns those two objects, and then you pass those same objects into this class, which also has its own aEnter function that returns like a session object, and this object is the one that exposes those functions, and every one of those functions actually defined as async def. This is why you can use await with them, because the call tool itself is defined as async def, not just as def. A little bit complicated, but I mean, good to know, I would say. So those two objects are passed to the client session constructor, which is another context manager object with its own aEnter function that returns a session. The session exposes a couple of useful functions like call tool and read resource. So as mentioned before, the code here is almost all sequential, no background tasks are created, so await really just waits. As mentioned before as well, the concepts covered in this lecture will be even more clear when we cover generators in a later lecture. Okay, so are you annoyed yet? I suppose yes. Dealing with async execution on that low level can be quite annoying, especially when the system becomes larger and more complex with a lot of agents and a lot of nodes and so on. So this is why people prefer using high-level frameworks like LangGraph. So LangGraph abstracts a lot of those details from you, letting you focus on the high-level agentic design. So I mean, I was just trying to give you an idea how you would need to like care about all those details if you create everything completely from scratch. Like LangGraph just helps you. In addition, you are not only required to use LangGraph. I mean, there are a lot of frameworks, and actually Anthropic provides its own high-level Claude Agent SDK, which is different from the Claude Messages API. So the Claude Agent SDK can also significantly reduce the complexity for us. So more on that later. This is actually a very important part of the CCA exam. We'll spend a lot of lectures on the Claude Agent SDK. So it is still, in my opinion, super useful for you or for architects to have a good understanding of what's going on under the hood. And by this, this is the question, this is the answer, and see you in the next lecture. Okay, now with question number 6. You are a lead architect implementing a file refactoring agent. You need to ensure that the agent has the capability to modify files and run tests, but must strictly prevent the agent from executing any arbitrary terminal commands. Which of the Claude Agent SDK features do you think is the best to enforce this requirement in a scalable way? So A, make the system prompt clear that the agent can never execute terminal commands. B, explicitly add the bash tool to the list of disallowed tools. C, restrict the allowed tools and use a default permission mode. And D, implement a pre-tool use hook to intercept the bash tool call and prevent the actual command execution. So there are a lot of new things and new terms here. The goal of this question is actually to introduce the Claude Agent SDK and specifically talk about tools within the Claude Agent SDK. So we previously talked a lot about the Claude Messages API. So the Claude Messages API is low level. It is a stateless API that you must manage yourself. For example, as we saw earlier, you need to append each new message to the messages list yourself manually before sending a new prompt because the API is stateless. You also need to handle all the ping-ponging yourself as well. I mean, send a prompt, receive a message asking for a tool used, execute the tool yourself, then append the messages to the history and send another prompt and so on. So you can manage it using pure Python code like we saw in previous questions or using a higher level framework like LangGraph. However, Anthropic also gives you access to a higher level API called the Claude Agent SDK. This gives you a high-level autonomous agent out of the box with minimal boilerplate and minimal ping-ponging on your end. It's a little bit similar to how we did the same thing with Pydantic and we removed a lot of boilerplate, but now we actually use the Claude Agent SDK because in this exam it is asked a lot about the Claude Agent SDK. It's extremely important in the exam. So using this SDK, the agent can automatically do multiple rounds of agentic think, act, observe iteration. So think, like the reasoning, and then act, actually the agent or the LLM tells you, I need to call this tool. So you act and call this tool, and then you observe the result from the tool, and then you think again and so on. So it's called the think, act, observe loop. It has access to some predefined standard tools and skills to see its job done until completion. So tools, for example, tools to create, read and modify files. Those are standard tools. Tools to run terminal commands, tools to search the web and so on. So those, you can think of those as pre-built in tools that are there for you without you doing anything about it. You can also define some custom tools and also skills as needed, and we will talk about skills like later on. For now, let's just focus on tools. So Claude's official documentation provides a list of built-in tools. So we will talk about some of them in detail later, but for now, let's just have a look at some of those tools that are there by default. So you have like read tool, edit tool, write tool. So those are for reading, modifying, and creating files. You have search tools like glob and grep to find files by like pattern and search content with regular expressions. You have the bash tool, which is extremely important because if you have a bash tool, you can run any command in the terminal. So this is like a very, very important and very like strong tool. So run shell commands, scripts, get operations. I mean, bash is extremely important. You also have some custom tools for web search and web fetch to search the web and fetch pages. You have some tool search tools, so to dynamically find and load tools on demand instead of preloading all of the tools. And then you have some orchestration category tools like agent and skill, ask user question and to do right. So for example, if you would like to spawn some sub-agents and every sub-agent can do something different, you use the agent tool that is again built in and provided to you by Anthropic, and we will talk about sub-agents extensively later on in later questions. And we'll also talk about skills extensively. So if you are familiar with the coding sessions using Claude Code, the autonomous coding experience is powered by the Claude Agent SDK. So if you are using Claude Code itself, this is built using the Claude Agent SDK. However, Anthropic still provides this SDK for you in case you would like to use it in your own product, not inside of Claude Code. So as of 2026, Anthropic provides an SDK interface in Python and in TypeScript. So how do we use that SDK? So this is an example, this is a minimal example in using that SDK. So conceptually it is clear, even though the syntax might look a little bit confusing for now. The important thing to note here is this simple code actually performs multiple turns of think, act, observe automatically. So we still use Async IO, but now we use something new that is Async 4. I mean, we covered Async Def before, we talked about coroutines and so on, but now we have Async 4, and we will talk about this in actually a later lecture. I think it is the next lecture when we cover generators. So the most important thing in this lecture is this query function. So you use this query function all the time when you use the Claude Agent SDK. So this query function, you actually give it a prompt like find and fix the bug in this file, and then you give it an options like entry, and you use Claude Agent options that you import from Claude Agent SDK, and then you can give it a list of allowed tools like read and edit and mesh. So you are allowed to use those tools. So again, ignore Async 4, just think on a conceptual level for now. You actually send this query and you can get multiple messages, and we just print those messages in this case, okay? Okay, so the most important function here is the query function. The query call returns what we call an asynchronous generator. We'll cover this in detail later on. To fully understand the syntax, we need to a quick refresher on Python generators, which will happen in a later lecture. Let's focus on high-level tool permissions this lecture. So in this lecture, let's just focus on tool permissions, okay? So let's talk about tool permissions. Putting a tool in the allowed tools list means you are explicitly giving permission to the system to call that tool without asking for permission. It is auto approved. Again, if you use like Copilot or Claude Code, sometimes you will see the agent asking you, do you really want to do this? So this is asking you for approval. But if you have a tool written in the allowed tools list, it is auto approved. It will not ask you for it. Now, depending on other tool permission configs that we will talk about, the model can still request calling other tools that are registered but not explicitly whitelisted. So if you put a tool in the allowed list, you are explicitly whitelisting this tool. This doesn't mean that any other tool that is not whitelisted can never be executed. Actually, it can, but depending on some other configurations, the agent might just execute it automatically without permission, or it might ask you for permission. It really depends on how you configure the entire system. So for example, you have some built-in tools or tools in a registered MCP server that are not all whitelisted. So you should configure the system to let it know what it should do if a non-whitelisted tool is called. Okay. So similar to the allowed tools option, another option called disallowed tools is used for blacklisting. So putting even a built-in tool in the disallowed tools removes the tool completely from the tools available to the model. So this is a hard block. So this is now blacklisting versus whitelisting. So note, however, that a robust whitelisting approach is generally considered safer and more preferable, especially with dynamic tool discovery. It is not easy to list every single dangerous tool, and this specific point actually is a key point to answering the original question. Because you might be tempted to put the dangerous tools like Bash, for example, into the disallowed tools list. This is not super bad, but it's also not the best. Especially if you have dynamic tool discovery, you might have another tool that is even more dangerous than Bash, and you can't really keep just manually putting all the dangerous tools in the disallowed tools list. This is not very good or not very robust. So really generally prefer whitelisting tools over blacklisting tools. but the option exists. So in this example here, in the Claude agent options that is given as parameter to the query function, you can also have this allow tools equals bash. So this is a hot block. Okay, so tools that are neither in the allow tools nor this allow tools fall back to two other config options. So you have two other config options that you can send to the query function. One of them is called permission mode, and one of them is called can use tool. So permission mode, this can be one of predefined strings. So we will talk about this in a minute. Can use tool is another like parameter that where you can actually define a custom callback function that you can implement yourself. You can implement custom logic to allow or deny a tool call. For example, you might not want to allow bash in general, but maybe you can allow just one specific bash command. So you need to really have more complex logic. Or maybe you don't want to allow editing files except if those files are like documentation files. You have the extension .md, for example, or .txt, but you don't want to allow modifying like Python files. So really, you have full control here. So permission modes, you have a couple of permission modes. This is directly from the Claude documentation. So permission modes provide global control over how Claude uses tools. You can set the permission mode when using the query function or change it dynamically, okay? So you have a couple of modes. For example, default, this is a default mode. This is what I described. So this mode means no auto approvals. Unmatched tools trigger your can use tool callback, okay? You have a mode called don't ask. So this denies any tool that is not pre-approved by allowed tools or rules is denied. So can use tool in this mode, can use tool callback is never called actually, it is auto denied. You have another mode called accept edits. So this auto accepts file edits, okay? So you have another one called bypass permissions. So this bypass all permission checks. So all tools run without permission prompts. So this is very like permissive. So use with caution. And then you have a plan mode. So read only tools run. Claude analyzes and plans without editing your source files. Okay. And then you have auto, which is only for TypeScript, not for the Python SDK. So model classified approval. So a model classifier approves or denies each tool call. See auto mode for availability. You can check that in the documentation. So this is a toy example of a can use tool callback. So you have, again, those are your options, Claude agent options. You have allow tools, you have this allow tools, but you also have this callback, can use tool equal my permission callback, and you must define this as async def as well. And then permission mode here in this example is default, which means that if there is a tool that is not matched, it will fall back to this one. So here, for example, if tool name equal write file, so this is not read or grep or bash, it's called write file for some reason. So here you have some custom logic. If the file ends with .py or .md, you actually return permission result allow. Otherwise, you return permission result deny. So only like allow writing files if the path ends with py or md in this case. You can also have a human in the loop for sensitive deployment actions. So if the tool name is equal to push to remote or push to remote repo, then you actually confirm. So input here actually raises something to the user. So the user confirm push to branch, this branch, yes or no, and then return allow if the user says why, otherwise just deny. If the tool is none of those, just deny. So strict fallback for unlisted tool. So this is one example of how you can use the can use tool fallback with permission mode equals default. So what if permission rules conflict with each other? So the Claude SDK follows a specific priority order. Again, you can see that in the documentation. And there's something called hooks here. That's the very first one. So we will cover hooks later. For example, there is a hook called pre-tool use hook. We will cover hooks later in detail because they are also a very important part of the exam questions. But this is roughly like the resolution order, if you might say. So first you run the hooks, for example, the pre-tool use hook. So if the LLM asks for calling a specific tool, you first run this hook. A hook can deny the call outright, or it can pass it on to the next check. So I mean, think of those as some sort of like a graph on their own, and you actually see the actual graph in the next slide. But really, a hook can deny the call or just pass it on. But if the hook allows the tool, this doesn't mean the tool must be executed, because the tool can still be denied by any of those. So you can think of a hook as something that can deny a tool call, but not force allow it, because it can still be denied by any of the next steps. Okay. So a hook that returns allow does not skip the deny and ask rules below. Those are evaluated regardless of the hook result. Okay. And to be honest, when you talk about hooks later on, a hook's main purpose is not to deny tools. I mean, this is a little bit of an anti-pattern. You should use hooks for different things, and we'll cover when it is best to use hooks. However, it can be used to deny tool calls if you want. Then after this, you get deny rules. So for example, if you have this allowed tools and settings.json, we will cover settings.json again later on. But for now, let's think of the deny rules or as being the disallowed tools. So if this tool is disallowed, it gets denied automatically. You don't actually go later on, okay? Even in bypass permission mode. So this is what I meant when the rules actually conflict, because you might have a permission mode of like bypass permissions, which means permit everything. However, if you have bypass permissions, but a specific tool is explicitly listed in the disallowed tools list, it still gets denied even with bypass permission. So the permission mode, then, if you actually pass those two, you reach the permission mode. So you apply the active permission mode. So bypass permissions will approve everything now, and it will not even try to check the next two ones. Accept edits approves file operations, other modes fall through. Okay, so if you have accept edits and the actual tool is file operation, then also this gets accepted, but other like modes fall through. Okay, then you have the allow rules. So check allow rules from the allowed tools and settings.json. If a tool is allowed, the tool is approved. Otherwise, at the end, if the tool is not explicitly listed in the allowed tools, you actually fall back to the can use tool fallback. So if not resolved by any of the above, call your callback for a decision. In don't ask mode, this step is kept and the tool is denied. Okay. So this graph actually makes this simpler. So you have a tool request. You first go into the hooks check. So you have pre-tool use, can deny. If it denies, it just denies. But if it accepts, then you don't execute. So you don't execute directly. You just pass into the deny rules. So if the tool is in this allowed tools or settings.json deny list, you actually deny, and then that's it. You don't pass into the next one. But if it is not in the disallowed tools, you actually check the permission mode. If the permission mode is bypass or accept edits, and the tool is accept edits, is an edit like tool, then you just execute and you don't pass in. However, if it is not bypass all, then you search or check if the tool is in the allowed tools. If it is in the allowed tools, you just allow and execute. Otherwise, you fall back to can use tool, and can use tool you can either allow or deny. So this is just the workflow if you would like. Okay, that's about those like standard tools, but you can also define a custom tool and use it in the exact same way. So how can you define a custom tool to use with the Claude Agent SDK? Anthropic actually allows you to create a custom in-process MCP server that exposes some custom tools. I mean, you can create an MCP server like we did before in a previous like lecture with the fast MCP like package or anything, and then just use it. However, Anthropic actually allows you to create a custom in-process MCP server. So this is a little bit simpler. You can think of it as a different approach or a different way to create an MCP server. So let's show one example directly from the Claude's documentation. So the Claude Agent SDK, here you can import tool and you can import create SDK MCP server. So this is how you can define a tool. So add tool using this decorator. The tool is called like get temperature, and this is the description of the tool, and those are the parameters of the tool. So now what you do in this specific example is you actually call using HTTP some specific like website api.openmeteor.com v1 forecast, and then you send on the params which you get from the arguments here, and then you get a response from this website, okay, and then you return this response in a format that is expected by Claude. So here this is the return format from your custom function, but this is just the tool, right? You need to create an MCP server to expose this tool. So here again you use create SDK MCP server. You name the server, so this name is the name of the server, not of the tool, and you have a version of the server, and then you have tools equal a list of tools. In this case we have only one tool, which is get temperature. So you define this in the same script as you use it if you would like to do that. I mean, you can do whatever you want. But in this example, we assume that you define this in the same file actually. So this is why we called it in process. Okay. So this is how you can use custom tools from this server. So the code snippet assumes the weather server is defined in the same file actually. So here we reference weather server. So we assume it is defined in the same file. The tool name to use is mcp __ server name _ tool name as per Claude's documentation. So you need to follow this. So allowed tools here, you actually need to follow this format because like Claude or Anthropic actually parses this string in expecting this. So you have mcp _ weather. So it already knows that this is the mcp server, and then this is the tool, the specific tool. So this is an allowed tool. And then async for message in query. Query is the most important function here. You can give it the options which actually have allowed tools, and then you can, what is the temperature in San Francisco, and then you can print this message. So this is how you define a custom tool. Okay, so this is the question again. You need to think about the answer. So you are a lead architect implementing a file refactoring agent. You need to ensure that the agent has the capability to modify files and run tests. You must strictly prevent the agent from executing any arbitrary terminal command. Which of the features do you think is best to enforce this requirement? I mean, in the actual exam, you might find sometimes that multiple answers make sense, so you need to choose the best out of them. And this exam is one example of those. So first A, make the system prompt clear that the agent can never execute terminal commands. This is a poor choice because system prompt is still at the end of the day probabilistic. The model can follow it or not follow it. You can't be 100% sure. You need to be 100% sure, right? You can explicitly add the bash tool to the list of this allowed tools. So this is definitely one option. It could have been a viable option if other options are bad. However, you still have option C where you can restrict the allowed tools and use a default permission mode. In my opinion, option C is better than B because we generally prefer whitelisting over blacklisting as we described, right? So B and C are both okay. And then you can also have D, implement a pre-tool use hook to intercept the bash tool and prevent the actual command execution. This is also actually possible to solve the problem. However, again, I mean, this is a question of intent at this point. Hooks, you can use it to deny tools. However, this is not really what hooks are meant to be used for. So again, it's like some sort of an intent at this point. So the best option out of those is actually C. And here I describe what I said, so let's just skip it. So why option B is not good, why option D is not good. I mean, hooks can deny execution, but their main goal is to have side effects like observation and transformation. So you can use hooks, for example, to make sure that the inputs to the tool are like as you expect, or like to transform them, for example, convert, let's say, from integer to float, or from meter to inch, or like do something like this if you want, or just to run observability, just to have some logs, to push some logs to a server or to a file to say that, you know, this tool now is being requested to be called blah blah blah. You can do this. So this is what hooks are mainly for. So using the wrong tool for the job is anti-pattern even if it works. And this is all what I wanted to say in this question. See you in the next one. Okay, now with question number 7. Which of the following is false in the context of the Claude Agent SDK? First, setting permission mode to bypass permissions will still not allow a tool to run if it is in the disallowed tools list. This is actually true. We covered this in a previous lecture, so this is true. B, a turn is defined as one round trip inside the agentic loop. Claude produces an output that possibly requests one or more tool calls. The SDK executes those tool calls, and the results are fed back to Claude for the next turn. Turns continue until Claude produces an output with no tool calls, at which point the loop ends and the final result is delivered. This is also true. I mean, we didn't cover it before, but this is the definition of a turn in Claude's documentation, so you should know that. C, in Claude agent options, you can provide a max turns parameter that limits the number of autonomous turns the agent can go through to avoid burning tokens indefinitely if the agent is stuck. This is also true. We also didn't cover this before, but it is important that you know this. So you can define a max turns to be 10, for example, to avoid like looping forever. And finally, the query method returns a standard Python list of messages that can be accessed only after the model has finished its entire agentic loop and reached a final result. I mean, since the previous three are all true, this must be the false one. And indeed, it is false because the query method does not return a standard Python list, it returns a generator. And this lecture is about Python generators. Okay, so D, this is the correct answer. And I guess, yeah, this is what I said. So let's actually start talking about Python generators. So generators can be synchronous or asynchronous. For the Claude SDK, you actually use asynchronous generators, but let's first cover synchronous generator. So let's remember our simple SDK example that we would like to understand. So how can we interpret this syntax, specifically the async for message in query? So let's try to start with the synchronous generators. So a standard synchronous generator is a function that uses yield instead of return. So for example, this one, def, and this is def, not async def. So this is just synchronous generator. So def sync generator, and then you can yield. You can have multiple yield statements instead of like multiple return statements. I mean, typically you wouldn't write multiple return statements after each other, but you can write multiple yield statements after each other. If you're not sure what yields are, I'll explain those right now. So when you call this, the function does not run the code immediately. It returns a generator object that you can iterate over. So this is very similar, if you remember, this is very similar to what we said about if you define an async def function. When you call this function, you returned what? You returned a coroutine. Here you don't return a coroutine, you actually return a generator. So it is not the same. This is not the same. This is something different. It looks a little bit similar, but it's not really the same. So every time you call next gen, so you have this gen object, and then you can call next gen, the generator actually like starts or continues execution until it reaches a yield statement. It then kind of returns that yielded value. With the next call to gen, to next gen, sorry, so like if you go here now, with the next call to next gen, it resumes execution where it stopped. It does not start execution from the beginning of the function. It actually starts right here, and then it can do some logic, then yield the second like object here or the second string here. So if it runs out of yields, it just raises a stop iteration. So you can think of it as you actually start a function and then you are allowed to return something in the middle of the function, but then you can kind of recall the function again using next gen, but you don't start from the beginning of the function. You actually start where you stopped. You do some more logic, so you can have multiple like logic statements here between those yields, and then when you reach another yield, you actually return, and this is what you print here. So this second one, print action 2 fix bug, and then the third one will print action 3 run tests. And then if you call next gen again and there is no yield, then you get a stop iteration exception because the generator is empty. So this looks weird. I mean, why don't we just use functions? We'll talk about this now. So, but before that, instead of manually calling next gen, you can simply use a for loop, and the for loop here in Python is smart enough to actually end the loop automatically if the generator raises a stop iteration. So here you will not see the stop iteration. So this is just a for loop, for item in gen. So this is a generator, just loops over this generator and then just yields those and prints them. And then when the generator actually raises stop iteration, you just stop without the user seeing an exception. Okay, so this really does the exact same thing. And here, if you use the for loop, you actually don't use next. You don't use next in the for loop, you just loop and next is applied automatically for you. Okay, so why use generators at all? I mean, there are multiple reasons, but one of the most common reasons that is used all over the place would be memory efficiency. And this is used a lot in deep learning. So suppose you have a data set of 10 million videos that you would like to use to train a deep neural network. So you have, let's say, a CSV with 10 million rows containing video paths and some metadata and some labels and so on. So loading 10 million rows is not that bad. I mean, those are just text rows, right? So some paths. So this is not a huge memory. However, loading 10 million videos into memory, where every video could be like 1 gigabyte or like 10 gigabytes, that's huge, right? So you typically wouldn't want to load 10 million videos, but you are fine with just loading 10 million rows in a data frame. So typically you don't want to load the entire 10 million video data into memory at once. Instead, you can create a generator that yields one batch at a time. So a batch of 64 recordings. You do a training iteration, like one backpropagation step or one training step. Throw this batch away. Actually, this is throw, not through, sorry. And then load a new batch. So this is a pattern that is used in data loaders for deep learning. So this could be one way of doing this. So you can create this generator, and actually Python is smart enough to know that this is a generator when it sees the yield statement here, because it just looks like a function, but it really understands this is a generator when it sees the yield here. So this generator here, you create a data frame, you just load the CSV. This is loaded only once. And then you have this loop. Inside this loop, you do some stuff and then yield tensors and labels, so like X and Y or targets. And then batch df, you just slice the data frame here from I to I plus batch size. And the loop here, you actually increment by batch sizes or chunks. And then you actually load the tensor. So here you actually load MB4. So this is where you load the actual video data or video binary data into memory. Just, this batch size. So you actually use batch df, not df. And then you actually get the labels from the batch df. And then you return, the videos and the labels. And then you actually define this generator. So data loader is equal to video batch generator. And then you get Ahmed Farhi custom data set CSV, for example. Batch size is 32. And then you actually loop over this generator. This right here is a generator. Okay, so you loop over it. You do a training step and then print something. And then the loop continues. So you get the second batch, the third batch, and so on until this loop ends, in which case it will just raise a stop iteration. And this for loop here will just consume it and it will work, right? So this is one very famous use case for synchronous generators. So a possible point of confusion here is this the same as Async Bosing execution on await? The answer is no. This is really, it doesn't have anything to do with Async. I mean, the term yield is used in both cases. That's true, but the situation is really different. In Async we have an event loop. When we use await, the entire task gets paused if we have some yield, some internal yield, right? and another ready task resumes execution. So there is some sort of an orchestrator of tasks that is the event loop, a task manager or a job queue manager, right? In synchronous generators, no waiting happens. I mean, the flow continues naturally. There's no event loop here. There's no async IO. We are not waiting for a long running process to finish and notify us, right? So this is a very big difference. So, which actually leads to a question. I mean, what if inside a generator, we actually need to call a process that takes time and wait on it, like allowing other tasks to run in the meantime? For example, we can, inside a generator, we can try to have a slow network request to an LLM or to a server or an IO operation. And this is where we get asynchronous generators. So asynchronous generators, you will have both yields together, which is a little bit weird. So let's read here. For async generators, the function should use the async keyword, so async def. This is what we had before with async IO in general. So because we would like to use await inside of it, and as I said before, this actually converts this like function into a coroutine as well. And then instead of next gen, you actually use a next gen in this case. So this is like the syntax. And instead of stop iteration, you actually get a stop async iteration. Okay. In a real application, instead of async io.sleep1, we will have a real network call or a time-consuming action. So let's actually have a look at this. So now we have async io.run main, and then main is defined using async def because we are using async io. Okay. Then we have gen equal async generator. So this creates the generator, but actually to execute it, it is not enough to just use a next gen. You still also need to use await a next gen, right? So I mean, you have now two things. You have a generator and you have a coroutine as well. So to run the coroutine, you actually use await as we described before in a previous lecture. So you have await a next gen. And when you call this one, it will actually start executing. And here you could have some sort of an LLM call or something. So this one internally will have some sort of yield as well, trying to tell the async IO that please try to schedule something else while I continue this network like request. And then when this is done completely, so you have await, this means that you will never go to yield except if this one is completely done. But I'm trying to say that while this is done, the like event loop can do another background task. Although again, in this specific code example, we didn't create any background tasks, so this is really a little bit synchronous. However, I mean, yeah, we will eventually, this like network call will end and we'll have some results, and then we can yield those results. Here I'm just yielding some string here. So yield here will be printed, so this string will be printed. And then we have await, and then some other network call or LLM call, and then again the event loop can, if it has other background tasks, it can run them, but now it doesn't. And then we yield another one, and then we yield another one. So here you actually like combine async IO and await with like generators, so you have asynchronous generators. And the nice part about this, I mean, if you think about LLMs or about the Claude agent SDK, you have those turns, right? Like the LLM will produce some result or some message, and then you do some call tuning and then return back, and then you produce another message. So you really don't need, if you use this asynchronous generator, you can yield internally. I mean, this is what Anthropic does internally. We don't have access to the internals of the query method, right? But internally, at some point, they will just yield something, and those messages will be like streamed, will be yielded one by one in a way, as they are ready, because you know an agentic like workflow or like process can actually take multiple minutes, multiple hours, multiple days if you would like, and you would like to hear like feedback, so you can yield different messages as they get ready for the user to feel like interactive. So the loop version of this would use async for. So yeah, so here we used await a next gen. So this is the non-loop version, but you can use async for, and this is really what we use with the query method. And this does exactly the same thing, right? Okay, so async for here, like one time it will yield this one, and then will yield this one, or like print this one since we print here, and then we'll print this one. And obviously in a real application, here you will have something that like a network, an LLM call, and then you have a response and just print this response or something, right? Okay, so hopefully we are now in a position to understand what's really going on with the Claude Agent SDK. So think of query as a function with multiple yield lines. It returns actually an asynchronous generator, and then you can have async for message in query, and the query could keep doing whatever it is doing, and at the same time you can still like print the messages as they arrive, which is nice. So this is a toy implementation of what the query method might look like. The real implementation is obviously handled by Anthropic. So here is async def query, and then for example you have something, and then you yield, and then you have something like for example if you have some allowed tools, and actually the LLM wants to use a specific tool that is read, then you do something else, and then you yield, and so on. So this is really a very wrong example of the query method, but it gives you an idea of what I'm trying to say. So this is the answer to the question. The query method returns a standard Python list. That is not correct, right? Because it returns a generator. Now, I also would like to say that for the Claude Certified Architect exam, they will not ask you about syntax. I'm just explaining those things for you to really understand what's going on under the hood. And by this, see you in the next lecture. Okay, welcome to question number 8. You have been hired as the lead AI architect for a firm that integrated a serious number of specialized MCP servers during a period of aggressive AI expansion into their customer-facing AI-powered product. Those servers are billed based on the number of monthly requests. The CEO has launched a Lean AI initiative to cut costs and assign that to you. You believe in open source, and you argue that most of those expensive MCP servers have open source or like flat fee based alternatives. You would like to start refactoring, and you decide to start with the most invoked servers first to have the biggest short-term impact for the next company meeting. How should you work through this problem? Okay, so you have 4 options. First, use a user prompt submit hook. On every prompt, append a clear instruction asking the agent to log MCP tool calls, if any, to a dedicated database. B, use a session end hook to do the logging. On each session end, run a script that reads the entire context, searches for tool usages, and saves them to a dedicated database. C, configure the Claude agent option with auto log tools equals true. This is automatically supported by Claude since logging is an important part of any serious product. And D, implement a pre-tool use hook with a hook matcher for MCP __ to log every tool invocation attempt to a centralized database. Okay, so this question is clearly about hooks, which is extremely important in the exam and in general for your workflows. So hooks are callback functions that run in specific fixed parts of the pipeline, like before or after a tool being called, session starting or execution stopping, and so on. So typically you would create hooks as some deterministic functions. However, you can, if you want, implement an LLM call inside a hook depending on your use case, because at the end of the day, they are just callback functions if you are using the Claude Agent SDK, so you can do whatever you want inside a function, but generally it is preferred to just make them some deterministic functions. So some common use cases for hooks are actually available in the documentation here. So when should you use hooks? So for example, you can block dangerous operations. So before they execute, like destructive shell commands or unauthorized file access, although as I said in a previous video, I mean, you can do that using hooks, But if you can do that using like the permission mode and so on, it is generally like more in the intent of the permission mode, not of hooks. However, you can definitely use hooks to do that. I mean, this is the documentation, right? You can use hooks to log and audit every tool call for compliance, debugging, or analytics, and this is extremely important. I would say this is one of the most use cases for hooks, is you would like just to understand whatever is going on, right? You can use hooks to transform inputs and outputs to sanitize data, inject credentials, or redirect file paths. So for example, maybe you would like to do some changes to the inputs of the tools before you call the tool, or do some standardization to the output of the tool after the tool is run or something. So you can use like pre-tool use hooks or post-tool use hooks to do this if you want. You can also use it to require human approval for some stuff or to track session lifecycle. So you can read more about this in the documentation depending on your use case. So the documentation provides a list of currently supported like hook events. So we have a couple of those. We'll just walk through them one by one such that you are aware of what exists. For example, you have a hook event called pre-tool use. So you can run this, or this one actually, you can hook something or hook a callback whenever a tool is being called or before a tool is being called, and you can obviously like have a matcher to try to run it only for specific tools if you want. For example, only for the edit tool or the bash tool and so on, and we will see some examples. So you have pre-tool use, you have also post-tool use, you have post-tool use failure, and you have post-tool patch. You have a user prompt submit, for example, so this one will run whenever a user like submits a prompt. You have a stop, like where like you can run this hook whenever an agent execution stops. Sub-agent start, and we'll talk about sub-agents later. Sub-agent stop, okay? Pre-compact, which is interestingly important. I mean, if you are familiar with working with Copilot or like Claude Code for development, whenever you have been working with the agent for a long time, the context window gets filled and then a compaction event happens. So this really tries to compress the context in a smart way. But then before the compaction happens, you can actually do something like you can ask like the agent or the workflow or Claude Code for this matter to just try to dump the, for example, dump the current context or something before compaction, right? You can do whatever you want in this case. You also have some more like permission request, session start, session end, notification, setup, teammate idle, task completed, config change, work tree create, work tree remove. I mean, work trees are get features that are nice. They allow you to like work on multiple branches without like complexity. I mean, this is a get feature, not a Claude feature, but it is nice actually that you have specific hook events for get in this case. Okay, again, you can read more about those in the documentation. So, I mean, so far in the previous like lectures, we have been giving more focus to the Claude Agent SDK, right? Mainly the Python API. However, as we said, we also have like TypeScript API. But this is not the only thing where hooks, or the only place where hooks can be applied. You can actually use hooks with Claude Code itself. So now you are a developer using Claude Code, not really just like a developer creating a workflow using the Claude Agent SDK. So you can use hooks in both those configurations. So don't forget that Claude Code itself uses the Claude Agent SDK. This means that you can use hooks during your typical code development using Claude Code, even if you are developing just a web application or something. So you don't need to be creating an agentic application to use hooks. Using hooks inside Claude Code is a bit different though, so we'll cover those differences. So in the Python SDK, you define the hooks as callback functions, and we will see the parameters and the return values of those functions. However, if you are applying hooks while working with Claude Code, you typically define hooks as scripts in your project and put commands to run those scripts in a standard Claude settings.json file, which is an important file that we'll talk about right now. So I mean, those are two different ways of creating hooks, and those scripts can be like bash scripts or like Python scripts or something. So An example for an instruction to use a pre-tool use hook for Claude code written inside the .claude/settings.json file would be like the following. So here this settings.json file is an important file where you can define some configurations, and you will talk about different versions of this file. But I mean, here you can have this object here, and then you have hooks key, and then for every one of those events that we talked about in the table, you can say that pre-tool use, and then you have a matcher for the actual like tools where you would like to run those hooks, right? So now for the edit tool, write tool, and multi-edit tool, you would like to run those this list of hooks, and here the list has one hook, and here this one is of type command, and the command is just Python 3, and then run this file, which is a file that you wrote yourself or downloaded from some place. So note here that you can use a Python script, sh script, or others. Note that the matcher value is expected to be a regular expression. For pre-tool use, this regex matches against the tool names. For other hooks, check the documentation on how to match. So matching is important to avoid unnecessary hook calling on irrelevant tools. Okay. So there are multiple possible files with this JSON snippet, each with its own priority in the case of conflict, and this is very important. The exam will probably have some like questions on this. So you can put this settings.json under, like here, this is the home directory, and then /.claude/settings.json, or inside your own repo, inside your own project, you can just create .claude/settings.json. So I mean, remember this here is your home directory. And then this is inside your project, and then you can also do something like .claude inside the project as well, settings.local.json. So this one right here is called user settings, this is called project settings, and this is called local settings. With the priority in case of conflicts, I mean, you can define different like things in different files, in different settings.json files. Local overrides project and user settings, so this one actually is the final like judge in the case of conflict. Project overrides user settings, and user applies when nothing else specifies the settings. So this is really in order to make your workflow easier and to facilitate working with teams, right? So generally in a project, you can have this file, and this file can be version controlled and pushed to remote. So this is really specific to this one project. If you have some user settings, those user settings apply to multiple projects. I mean, if you have a lot of projects using Claude Code, this is like what you use, right? But then maybe for one specific project, you would like to tweak things a little bit differently. You might use some different tools or some different configuration. So this is why project settings went over user settings. And this is the only one that should get pushed to remote if you have like a remote GitHub repo or GitLab repo. But now you might actually want to do something your own way, like you would like to run some different checks that your team doesn't want to use. So you can actually override this one using settings.local.json. You are now telling Claude Code, I know what I'm doing. I know that my team uses this, but I really would like to use this because I'd like to run extra checks or something. So that's why local settings actually win over project settings. So note that for team collaboration, only .claude/settings.json should be committed and pushed to GitHub or GitLab. The other files are for your local preferences. Okay, so let's look at one possible like hook script. So here we actually have a Python file as a hook, right? So this is one way this Python file could look like. You actually receive the inputs to the hook. I mean, every hook, in order for it to operate, you actually need some input, right, to do some checks. And the input is actually installed or inserted automatically by Claude Code into stdn. And this is why what you do in your like script is you first actually load whatever is in sys.stdn, and this will be in JSON. This happens again automatically. Remember that here you actually don't pass any parameters. However, under the hood, Claude Code will actually insert the parameters inside some JSON, and then you read this JSON, and then you can do whatever you want, right? So do some checks and so on. And then you can either like return 0 or 2, right? At least those are the standards. So status 0 means proceed. For example, if this is a pre-tool use hook, status 0 means proceed, and status 2 means like halt the tool execution in this case. So this is again in the documentation. Exit 0 means success, exit 2 means a blocking error, any other exit code is a non-blocking code. Okay, and again you can read more about this in the documentation. So, but what about the input to the hook? How do we know the JSON format to expect? I mean, Claude Code will insert some JSON, but how do you understand what are the fields of this JSON? Again, you need to consult the documentation. This is well documented, the documentation. Here I have the link. But in general, each hook receives its own different set of inputs. So the documentation will tell you, for this event, those are the inputs that you would expect. And for this like other hook, those are the inputs you would expect, and so on. So, and also like moreover, tool hooks can receive a different set of inputs that depends on the actual tool. For example, the bash tool could receive different inputs to the edit tool, and this makes sense, right? So again, we will see some screenshots, but you can see the documentation here. So note that Claude Code automatically formats this input for you and sends it via stdn. You don't need to do complex parameter passing inside settings of JSON. You just read stdn in your hook script and it will have the correct input parameters. So for example, I mean, all hooks have some common input fields, and then specific hooks will have extra specific parameters. For example, in general, those will be sent to you by Claude Code for all like the hooks, like session ID, transcript path, current working directory, permission mode, effort, like are you like low thinking or medium or high thinking, and hook event name, okay? But then for example, if you have the breed tool use hook, which runs after Claude creates tool parameters and before processing the tool call, so matches on tool name, bash, edit, write, blah, 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 or MCB tool name. So, I mean, those are the matchers. We'll talk about matchers later. However, the input for this actually kind of depends also on the actual tool. For example, for the bash tool, you will receive some inputs, which is the command, for example, that you will want to run in the terminal, right? Description, timeout, a boolean to dictate whether you would like to run in background or not. For a write tool, you actually need, because this creates or overrides a file, so you need some extra special parameters, which file you would like to create or overwrite and what content you want to put in that file. So those are parameters specific to the write tool. For edit, you have the file path, the old string, the new string, and then replace all, which is a boolean, false or true, again specific to edit, and so on. So I mean, this is just a very rough idea. If you would like to dive deeper, you need to consult the documentation, but this is a very rough idea. And obviously the tool outputs or the hook outputs actually also like print stuff into stdout as JSON, and we will cover the outputs of the tool as well. But I mean, we covered this for Claude Code. What about the Python SDK? So the concepts are identical, but the implementation is a bit different. Again, you have the SDK documentation for hooks for more information. But in general, like a Python SDK hook should follow this contract, and we'll have example in the next slide. But really, this is just a function, right? And this function will take on some parameters as input and is expected to return specific output format. So for inputs, for example, you have those three inputs, and you have some parameter called input, and this one should follow the hook input. And again, this will be a little bit different based on the actual tool. And then you also have tool use ID and context. And from the hook, you are expected to return a hook JSON output, and we will see that as well. And this one can have like a couple of keys, like a decision, like a system prompt, and then a hook specific output, which is another JSON. So it's a little bit complex, but again, using the documentation, you will find out how to exactly use that. But this is one example. So here, this is a hook, right? So this is a hook that we define as async, def, protect, end files. And then those are the inputs. As we said, you have those three inputs, standard, and then this input data is of type hook input, and we'll see what this means, but this is some class, okay, that we actually import here. You have also tool use ID and context. Then you do something and you return an object right here, okay, And here we only return hook specific output. So I mean this one, but we can also return extra things if we want. Okay, so like system message or a decision block to block this action if we want. However, you can also just return hook specific output, for example, permission decision deny. So there are multiple ways to deny execution, I would say. If you return an empty object, this allows operation. So note that here in the Claude Agent SDK, we don't use exit 0 and exit 2. In the script version, we actually use exit 0 and exit 2. A little bit of a difference. So this is how you define a hook. This is how you register a hook. Again, inside Claude Agent options, you have a key called hooks, and then you can define here a dictionary. So for pre-tool use, you can actually define multiple hook matchers. So this is a list of hook matchers, and a hook matcher takes two parameters here in this example: a matcher, this is a regular expression that we talked about before, and also the hooks. And the hooks are actually lists as well. So you can have multiple hooks bear matcher, and you can also have multiple matchers for each hook event. So for pre-tool use, you can have multiple matchers. For example, for write and edit, you would like to execute those hooks, but for bash, you would like to execute another set of hooks, right? And then you just send this those options like this. Okay. So the SDK documentation gives more information about different input types bear hook event, similar to what we had for the Claude Code version of hooks. So check this documentation for the Agent SDK. So I mean, they are a little bit similar, but also I mean, you have separate documentations for the Agent SDK versus Claude Code, but they are very, very similar. So for example, this tells you that this is the base hook input. So you have session ID, transcript path, CWD, permission mode. This is similar to the base that we had for Claude Code as well, right? But then for pre-tool use hook input, you actually extend this one. So you inherit from this one and you add some more stuff, right? So those are the inputs that you will get as input to your hooks. So you write your hook function assuming that you will get those inputs. You are guaranteed to get those inputs. Again, this is for the SDK. This is similar to what we said in the Claude Code version, where in your script you start by loading stdn and you guarantee that the JSON will have those specific inputs. For outputs, this is what you return from your callback function. You return some sort of a JSON. You can have some top level fields like system message and continue, but you can also return this hook specific output like what we did here. So here you return hook specific output, and then again you can return some specific parameters like permission decision, deny or allow, and so on. Again, for the details, you need to check the documentation because it is really different for every hook. So this is just an idea. And for the exam questions, it is probably, for most questions, probably enough just to know this idea, because the exam is focused more on you understanding what hooks are, not asking you about the exact specific parameters, except for some cases. But in general, this high level understanding is good enough. So if you return an empty dictionary, you allow the operation without changes. So you are not denying the operation or the tool call. And here the documentation tells you that the SDK callback hooks use the same JSON output format as Claude Code shell command hooks, which documents every field and event specific option. For the SDK type definition, see the TypeScript and Python SDK references. I mean, you can read the documentation. Okay, now back to our question. What is the answer to this question? So again, you would like to start refactoring and you decide to start with the most invoked servers first. So you actually would like to know, to find out information, which of those servers are used more often or most often, such that you start by replacing them. So actually you need to have a hook that logs. So a hook, a logger hook, that actually logs every MCB tool call, and for this option D actually makes more sense, and we will cover why A, B, C are less than ideal. So implement a pre-tool use hook with a hook matcher for MCP __ asterisk to look every tool invocation attempt to a centralized database. Okay, so correct answer is D. Remember, MCP tools are defined, we said this in a previous video, MCP tools are defined as MCP __ server name __ tool name. And since we only care about MCP tools, this is why we have a regular expression with MCP __ asterisk. We don't want to log non-MCP tools like Claude built-in tools. Why A is incorrect? So A says use a user prompt submit hook, and every prompt append a clear instruction asking the agent to log MCP tool calls, if any, to a dedicated database. So again, user prompts are not super reliable, not super deterministic, right? The LLM can just ignore this request, or if you have compaction, you lose context and you lose this request. And also this adds an extra tool call. So now you will actually have a tool call to do the actual like MCP server tool call, and you have another tool call just to log. However, if you use a hook, the hook runs, it's not a separate tool call, it's just like a function or a hook that runs before the MCP tool call. Why B is incorrect? So B use a session end hook to do the logging. On each session end event, run a script that reads the entire context, searches for tool usage, and saves them to a dedicated database. This is not correct, again, because it is anti-pattern, and also because you could have some compaction happening, right? Your session can be very, very long, right? And then compaction could happen multiple times, and with compaction, you can actually lose track of which tools were called, so it is not like reliable enough. Why C is not correct? So C tells you configure the Claude agent options with auto log tools equals true. This is automatically supported by Claude since logging is an important part of any serious product. This option is incorrect because there is no option, there's no such option as auto log tools equals true. So this doesn't even exist. This is just, something I made up. Okay, so this is what I wanted to say about hooks. See you in the next video. Okay, now for question number 9. You are building a customer support resolution agent using the Claude Agent SDK. The agent handles high ambiguity requests like returns, billing disputes, and account issues. It has access to your backend systems through custom MCP tools, like some tools like get customer, lookup order, process refund, escalate to human. Production logs show the agent frequently calls get customer when users ask about orders, like check my order 1, 2, 3, 4, 5, instead of calling lookup order. Both tools have minimal descriptions, like retrieves customer information or retrieves order details. What is the most effective first step to improve tool selection reliability? First, add few short examples to the system prompt demonstrating correct tool selection patterns with 5 or 8 examples showing order related queries routing to lookup order. B, expand each tool's description to include input formats it handles, example queries, edge cases, and boundaries explaining when to use it versus similar tools. C, implement a routing layer that parses user inputs before each turn and pre-selects the appropriate tool based on detected keywords and identifier patterns. And D, consolidate both tools into a single lookup entity tool that accepts any identifier and internally determines which backend to query. So this is actually a very simple question, but what is special about this question is this is part of the Anthropic practice exam. So Anthropic tells you that this is the kind of questions that you might face on the actual exam, and actually I think this is pretty simple, but it is nice for us to cover, okay? So this question is directly extracted from the exam question samples provided by Anthropic. So I'm just trying to say that not all exam questions are tricky. This is a simple one, so there are actually no new concepts to cover. So let's try to answer this question like directly, and my answer to this question would be B. Expand each tool's description to include input formats, handles, example queries, edge cases, and boundaries explaining when to use it versus similar tools. This is the correct answer. Okay, so why not A? Like A tells you add few short examples to the system prompt. So few short examples in general are like generally useful, are generally super powerful. However, the question is actually asking about the most effective first step. The question explicitly says that the tool descriptions are too short. So since that they are inherently confusing to the model doesn't really know when to call that tool versus that tool, okay? Remember, tool descriptions are still fed into the actual LLM in the prompt anyway. They need to be clear in order for the model to choose the correct tool. You should still provide some examples to the model, but the correct place is in the tool description, not in the system prompt. Why? Because typically you use a system prompt for high-level instructions. For example, to set the response style, the tone, the persona of the model, and enforce constraints. For example, tell it you are like a helpful coding assistant specializing in blah blah blah, and you are capable of 1, 2, 3, for example. Or always challenge my ideas if I am making a mistake. You are setting the persona here. Before choosing any tool, decompose a problem into smaller ones. So this is a high-level instruction. This belongs into the system prompt. You are a sub-agent specialized in sports. If you receive a question about politics, refuse to answer and clearly state your expertise. So this could also belong to the system prompt, although you can also use guardrails, like more deterministic guardrails for this case. Low-level tool-specific examples should be localized in the tool description. If you put this in the system prompt, it will quickly turn into a mess, especially as the number of tools increases. You can also imagine that the situation will become even worse if you use external MCP servers, right? Because then you have this dynamic discovery and you really can't control the number of tools, or maybe you don't control the number of tools that you receive with dynamic discovery. Maybe there are a lot of tools, a lot of MCP servers. You don't want to write every single tool description in the system prompt. Actually, the creators of those MCP tools should make sure the description is clear enough, and this will make the whole pipeline easier. Okay, so this is why not A. But why not C? C says implement a routing layer that parses user input before each turn and pre-selects the appropriate tool based on detected keywords. I mean, this is not really an LLM solution. So it can be valid on a system level, you can think about it, but it bypasses the autonomous LLM reasoning capabilities. So it is more of a deterministic engineering solution, maybe, or it could even like have some other like classifiers, small classifiers, or like keyword detectors and so on. So I mean, it is a solution to investigate. However, it is not really like using the full power of autonomous LLM. And to be honest, even then you still need to use machine learning. I mean, to be honest, I prefer to use deterministic solutions whenever possible. So if this solution or this option C was completely deterministic, I would have actually decided to choose that answer. However, you still anyway will have to use some sort of machine learning to find out the intent of the user. So if you are anyway using machine learning, then maybe try to make the tools or the tool descriptions better first. So D, why not D? So consolidate both tools into a single lookup entity tool. I don't think this really addresses the real issue here. The real issue is the descriptions are short. And what if we have 20 different entities? So, I mean, would we create a single function that handles 20 different entities? This doesn't look like the correct approach. So the answer is B. And this is all what I wanted to say in this video. See you in the next one. Okay, now for question number 10. Your team wants to reduce API costs for automated analysis. Currently, real-time Claude calls power two workflows. One, a blocking pre-merge check that must complete before developers can merge. And two, a technical debt report generated overnight for review the next morning. Your manager proposes switching both to the Messages API for its 50% cost savings. How should you evaluate this proposal? Option A. Use batch processing for the technical debt reports only. Keep real-time calls for pre-merge checks. B. Switch both workflows to batch processing with the status pulling to check for completion. C. Keep real-time calls for both workflows to avoid batch result ordering issues. And D. Switch both to batch processing with a timeout fallback to real-time if batches take too long. Okay, this is another very easy question, although we have new information to cover here. Again, this question is directly extracted from the exam question samples provided by Anthropic. Okay, so Anthropic actually gives you a new API called the Message Batches API, and the Message Batches API offers 50% cost savings, but has processing times up to 24 hours with no guaranteed latency SLA, where SLA stands for Service Level Agreement, which means there is no legal or contractual guarantees are given by Anthropic on latency at all. In reality, it often finishes much faster. So you really still send your request to Anthropic, but you can't send a lot of requests in a batch. And then Anthropic will not even try to respond to those like in real time. It can do those and respond within 24 hours. So this makes it unsuitable for blocking pre-merge checks. I mean, if you are familiar with like merging branches in GitHub or something, sometimes you actually need to run some checks before you allow a branch to be merged back into main. And you can, and we'll see some examples of that actually, you can use Claude to do some of those checks, some review or some checks. So you can use Claude if you want in some cases. But here, since this can take up to 24 hours, this is really unsuitable for blocking pre-merge checks, because this means if you have like multiple engineers trying to merge stuff and they depend on each other and so on, I mean, it will just become a mess. This needs to be real time, so you can't use the batch API for this. But it can be ideal for overnight batch jobs like technical debt reports in the question. So we are pretty much done with the question, but let me give you some details and some examples. So at the time of creating this slide, Anthropic allows up to 100,000 requests per one message batches request. So in the same request, you can actually send 100,000 messages. Also, the batch size cannot exceed 256 megabytes. I mean, you can imagine that some of those requests might be like heavy or long messages, or even include like images if you want. So this is why they also put a limit on the actual size of those of the batch. You can check this documentation for more up-to-date info in case things change in the future. I'm recording this in Q2 2026. So those are processed in parallel, so they cannot depend on each other. Everyone is processed completely in parallel. Moreover, this API does not allow agentic looping. So the LLM will process the message and just spits out an answer. This answer can request tool calls, but that's it. You need to investigate the batch results and decide on what to do next. You can't really loop back into the models and have this agentic loop. It's just like one shot. So depending on your tier, the total number of messages that can exist in the processing queue is also limited by Anthropic. For example, if you run 10 batch requests, each one has 100,000 messages. Anthropic will not allow processing 1 million messages in parallel, at least for the lower tiers. So this is an example of how to send this message. So you have like client.messages.batches.create. So you have this .batches here, and then you give an ID and you give some parameters and you give the messages and you give the model. So I mean, this is just the Python API here. And using that ID, you can retrieve the message batch object, which you can query for some information. For example, this is the object here. You can actually find the processing status and the request counts, how many cancelled, errored, expired, processing, and succeeded. And then some URL for the results. And then you can also get the results directly using the ID as well. And this is pretty much what I wanted to cover. So the answer to this question is actually going to be A. Use batch processing for the technical debt reports only. Keep real-time calls for pre-merge checks. So this is the answer. See you in the next lecture. Okay, now with question number 11. You are building an AI assistant for a hospital. The AI needs to read a doctor's messy notes and extract relevant information in a structured format, then run a custom Python script to make sure the formatting is 100% correct, then send an automatic request to the insurance company for medication approval. This is a repeatable process that should happen with each patient visit. How should you set this up using Claude's official features? So A, use a standard synchronous message.create request. Include the raw clinical notes from the doctor and in the prompt alongside the Python validation logic. Pass the insurance API definition in the standard tools array parameter to handle the external request to the insurance company. B, utilize the asynchronous message batches API by bundling the patient notes, the Python validator script, and the insurance tool schemas into a single JSON-L payload. Submit the file to the batch endpoint to process the extraction, execute the validation, and queue the insurance requests over the 24-hour target window. Option C, establish a directory-based workspace folder containing the required validation script and the insurance API caller script. Place a skill.md file at the root of the directory to define the repeatable steps, enable the skills and code execution features. D, define a custom tool that executes all the required steps in series. The LLM's responsibility is to figure out if it needs to call this tool or not. Okay, so this question is to introduce skills. In general, whenever you have a set of multi-step repeatable workflow instructions, the encouraged approach is to use agent skills with Claude. You can use skills in Claude code to improve your development workflow. In this case, the skills are not released to customers, it's just something that you do for development. But also, in addition, you can use skills for your own agentic software that you release to customers using the Claude Agent SDK. So again, you can use skills in both those formats. So for example, you can create some sort of an endpoint that the customer request goes to, and then the skill actually helps the LLM make a decision on some stuff. So you can use it for customers as well. So examples for using skills as a developer in Claude Code would be creating a skill to do code review, following an internal, clear internal checklist, a skill to perform the release process like build, then package, then test, then deploy. A skill to read an error log, create Jira tickets, assign to the proper team and notify them in Slack. So I mean, those are all forms of skills. Typically, the mechanics of it is you create a separate folder structure for skills inside .claude/skills for project level skills, or in the home directory /.claude/skills for user level skills. You can also have plugin skills if you install Claude Code plugins, which allows skill sharing and distribution. And in general, you can just download skills that someone else created and just put it into your folder structure. And there are a lot of skills that other people created as well. So under .claude/skills in this specific example, you create a folder for each different skill. So for example, you can have a folder called PDF extractor for the skill responsible for how do you want to extract stuff from a PDF. Another folder called code reviewer, and so on. So this right here is the folder structure. Note that this folder is auto-discovered by Claude Code and or the agent SDK, and this is why you should follow this format. The most important file in each skills folder is the skill.md file. This is where you define what the skill does and a clear step-by-step instructions on how to properly do the required tasks. You have a repeatable workflow in this case. So this is an example of a skill file, of a skill.md file. So as you can see, there are always two parts and you need to write it in this format. This is not free form. You need two parts separated by those 3 dashes here. The first part is called the YAML front matter, and you use YAML to write this. So you have keys and values. So you define the name of the skill, a description of the skill, and this is very important because this is what tells the LLM when to use this skill. And you can define some other like options. For example, here in this example we have triggers. So whenever the user writes, or whenever the prompt writes review my changes or run code review, this skill is expected to be triggered. And then you actually define the actual workflow, what the LLM is supposed to make sure happens. So first you tell the LLM you need to run get def head, if empty stop and notify user, and then the LLM will actually find out that this requires, for example, the bash tool. So it will trigger the bash tool with this command and then like try to find out the def, for example. Then run linter, so execute this right here, and this is a script that is put inside the code reviewer skill inside the skills folder. Right, so again you can define some scripts and then you actually ask the LLM to request calling those scripts. Again, this is going to be like executed in bash as well, or using the bash tool as well. Then read this file right here, so it is templates again inside code reviewer checklist. Evaluate the def for any discrepancies with the checklist for review, and then report, and then in report you can do those things as well. So this is where you define the workflow for the skill. So note that you have two main sections, the YAML front matter and then the markdown body. So this right here is markdown and this is the YAML front matter. Skills are context window efficient. This is extremely important for the exam and for your work as well. So unlike tools, when the system makes the LLM aware about the existence of specific skills, it does not load the entire skill.md file in the context window or in the prompt. So not this entire thing is copied as is into the like prompt. Only the YAML front matter is copied in the prompt. And this is important because it saves context window. You don't actually put this in the context except if you actually decide to use this skill, or except if the LLM decides to use this skill. Okay, so this way the LLM knows that the skill exists and when to use it, but it doesn't clutter its context window with step-by-step instructions until it decides it needs the skill to do something. So this is called progressive disclosure or lazy loading, and you might find those terms in the exam questions. This is why I put them. So progressive disclosure or lazy loading. If it decides it needs it, the markdown body is then loaded. So contrast that to the standard tools. If you register a tool, the entire JSON schema of the tool, including every function name, every argument, type definitions, and detailed docstring, is injected directly into the system prompt. So skills are more context window efficient. So are they deterministic then? The answer is no. Those are not bash scripts. So you can say, here is what you should do, but the LLM is not forced in any deterministic way to really follow those steps in order. It can still hallucinate, especially if it is a bad LLM. It can still hallucinate, but at the same time, there is a good view or a good perspective here, which is it can also be a little bit flexible. So it can try, for example, this one, and then the command fails for whatever reason, and then it can try something different. So I mean, this is a double-edged sword. So this is what I wrote here. So while you can write deterministic steps in the markdown body for the system to follow and for the LLM to reason, including requests to run specific scripts defined in the skill folder, there is no strict guarantee that the LLM will request those tool calls in order or at all. So this is a double-edged sword. It allows the LLM to recorrect or reorder the instructions if it faces unexpected inputs, but you are still in the world of stochasticity. So skills are not bash scripts. Your instructions are interpreted as strong guidance and get inserted into the LLM prompt with a strong wording to follow, but at the end of the day, no guarantees. So using skills with the Python SDK is also straightforward. So you define your skills folder structure as you would do with Claude Code. Then you either pass the parameter skills equals all or a list of approved skills inside Claude agent options. So here we have skills equals all, and you have some allow tools. But here you can also have specific skills that you allow for a specific query. for the Claude Agent SDK. So you can actually have multiple queries, and for every different query you can give access to different skills if you want, similar to the tools, which is nice. Okay, so now try to answer this question. It seems there is a repeatable workflow, and so obviously the correct answer is going to be C. So you actually create a skill.md file at the root of the directory that you create here for this specific workflow. Let's call it like insurance workflow or something, or insurance skill. And then you define the repeatable steps in this file. You have to enable the skills and code execution features. So this is the correct answer, answer C. Okay, but why not option D? So, I mean, option D says define a custom tool that executes all the required steps in series. The LLM's responsibility is to figure out if it needs to call this tool. So, I mean, this also can work. And in some situations, if you really don't need the reasoning power of an LLM, maybe this is really a better option sometimes. But again, as I said, the good things about LLMs, about using skills with LLMs, is if the LLM actually fails in one step, it can still reason and try to do something different. It can try to make it work. But if you are 100% sure that those steps should actually work perfectly, then maybe this can be an option. Although in general, you should think of a tool call as some sort of an atomic operation, not entire workflows, at least in the context of LLMs. So to define a workflow or a multi-step process, especially if it involves different tools like code checks, test runs, cloud deploys, things that are different, they are not the exact same thing. So skills are considered best practice, although I would like to emphasize here that this is pretty much only true if some of those steps actually require some LLM capabilities. For example, one step here is to read the doctor's notes and try to find some information. So you need an LLM for that. And also this is true if you would like to give some flexibility to your system where the LLM tries to do something and then it might fail, then it might try to do something else. You would like some sort of flexibility. If you don't want any kind of flexibility at all and everything is 100% deterministic, I think you should actually better use a batch script, not even a tool, not even a custom tool. It could be just a script and then you use the bash tool to run this bash script. So this really depends on your specific use case. For this question, option C makes more sense to me. And this is all what I wanted to say in this video. See you in the next one. Okay, now for question number 12. Working on a project using Claude Code, you realize you often need to manually reference a massive documentation body to get specific API functions for a custom internal software. You want to automate this lookup process so that Claude can seamlessly find and return the exact API signatures whenever you need them. Out of the following choices, which option should you try first? A. Create a new skill inside .claude/skills with detailed instructions on how to perform this research process. Option B. Append the documentation, the full documentation, directly into a custom system prompt configuration file so Claude always has access to it. C. Implement a custom semantic RAG solution so that Claude can get the proper APIs easily. And D. Build a custom sub-agent inside .claude/agents tasked with reading and parsing the documentation, exposing the result to the main session. Okay, so this question is mainly about sub-agents. So sub-agents are independent LLM agents that can be orchestrated by the main agent to do specific tasks. The most important thing to note about sub-agents is they have their own isolated context window. This is extremely important, and this is a double-edged sword. So on one hand, whatever they do will not clutter the main agent's context window, and context window is very, very precious. So they just do their thing and return a usable summary or a usable result to the caller/parent agent. On the other hand, any internal reasoning that the sub-agent did just gets completely thrown away in the main session. So this is why this is a double-edged sword. In addition, sub-agents can be run in parallel. So using Claude Code, the main agent typically decides to call a sub-agent automatically. Contrast that with if you are using LangGraph, for example, you create your own graph or your own like workflow, and you can decide that if you go from this node to that node, this other node has some sort of sub-agent, right? So you actually create the low-level graph in a sense. In Claude Code, you can do something like this. If you have like multiple different like API calls, you can create your own thing. But also, if you are using the Claude Agent SDK, you can just configure the sub-agents similar to the way you configure the skills and tools, and just let the system do whatever it deems like better. Okay? So you can even encourage calling an agent in the Claude Code CLI by directly using @agent name in the prompt, or directly instructing Claude to use specific agent in the prompt. So this way you can steer the behavior a little bit towards the agent that you want. You can also use Claude built-in sub-agents. So Claude comes with some built-in sub-agents similar to the way it comes with built-in tools, right? And you can also create your own sub-agents as needed. So Claude Code comes with a few built-in sub-agents. For example, the Explore sub-agent, which is a fast read-only agent optimized for searching and analyzing code bases quickly. The Plan sub-agent, this is another read-only, and when we say read-only, we just say that this sub-agent does not have access to tools that are able to modify things. Okay, so the Plan sub-agent is also another read-only research agent used during plan mode to gather context before presenting a plan. And then you have a general purpose sub-agent, which is capable for complex multi-step tasks that require both exploration and action. So this one is not read-only. There are some others as well, but you can create your own sub-agents as well if you want. So due to the isolated context property, sub-agents excel at tasks where the main agent only cares about the final result, not on how that result was achieved. For example, like in a repo, give me the file where authentication happens. You don't care about everything the sub-agent does, just care about this file. For example, what is a proper API call needed to send a batch job, which is similar to the question actually in this video, which is why this video is about sub-agents. Interestingly, sub-agents also are better for performing code reviews, and this is actually important. Like, think of it as a separate engineer reviewing Claude's code with a fresh eye. If you use the same agent that wrote the code to review its own code, it will be biased, and this is why it is actually best practice. If you write code using Claude and then you would like to review that code, don't ask the exact same agent that wrote the code to review it. You actually need to spawn a sub-agent for code review. So on the other hand, sub-agents are bad choices in cases where the journey itself also matters, where the reasoning steps also matters for later steps. For example, if you have a sequential pipeline of sub-agents with one agent to reproduce one bug, another agent to debug and analyze the bug, and a third agent to fix the bug, this is not a super useful pipeline actually. This is because the subsequent agents would benefit from the full context in the previous agents. This makes it better to just do this entire work in one agent context. The intermediate information matters, right? So sub-agents are not useful for all cases, which is obvious. But how do we create a custom sub-agent to be used in Claude Code? So the process is very, very similar to creating a custom skill. You create a file code whatever sub-agent name, for example, code reviewer.md, and place it under .claude/agents or home directory.claude/agents for project level versus user level custom sub-agents. Similar to the skill.md file, the file for the sub-agent has two sections: a YAML front matter section and a markdown body section. So this is an example of a minimal sub-agent markdown file. So the front matter YAML part is loaded into the main agent's context memory as part of the system prompt. So again, this is done automatically by Claude. All the front matters for all sub-agents are loaded into the system prompt or into the main agent's context. Okay, so this is how it knows what sub-agents exist. However, the remaining part of the file is not automatically like loaded. So it is good practice to only allow the minimal set of tools for the sub-agent. So here, for example, we define a sub-agent called code reviewer. We give a description, and then we give some tools here, and we give a model, Sonnet, right? And then this part, this like MD part, actually this markdown part gets ingested into the prompt of the sub-agent. So here you are telling the sub-agent, you are a code reviewer. When invoked, do blah, 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 right? So this part right here is to be injected into the context of the sub-agent, not of the main agent, but the front matter here is to be ingested into the main agent's context. Okay, so the description must be a single line, at least at the time of making this recording. It can be a super long single line though, so you are allowed to type /n if needed. The description field serves two main purposes. This description field right here, it lets the main agent know when to call a sub-agent, but it also lets the main agent know what to say to the sub-agent. So this description is mainly given or used by the main agent, right? So in this description, try to write it in a way that lets the main agent know when should it call a sub-agent or this specific sub-agent, and also what exactly should it pass to it. For example, so when the main agent calls a sub-agent, it creates an input prompt and sends it, right? You can influence this system prompt by modifying the description field. For example, you can write, you must give this sub-agent the list of files to review, for example, something like this. So the list of allowed front matter fields can be found in this official documentation, and key values include, obviously name, description, tools, and model, but also skills, disallowed tools, and also hooks. So you can ask Claude to make this file for you. Moreover, if you are using the Claude Code CLI, you can type /agents, and it will walk you through an interactive process to create a sub-agent. You can also use sub-agents with the Python SDK, but we will cover that in a later lecture in more detail. So now back to the question. Working on a project using Claude Code, you realize you often need to manually reference a massive documentation body to get specific API functions for a custom internal software. You want to automate this lookup process so that Claude can seamlessly find and return the exact API signatures whenever you need them. Out of the following choices, which option should you try first? So the most important thing here, it's a little bit subtle, but the most important thing here is you just need the API function. So you don't need the full context, and you do not want to clutter the context window of the main agent with this entire massive documentation. And this is why the answer is D. Build a custom sub-agent tasked with reading and parsing the documentation, exposing it to the main session. The main reason I choose this one is because this is massive documentation, and because I only care about the API calls. I don't care about how the sub-agent did the search and anything else. I just want the final result, and this is why sub-agents make more sense, and this is why this is actually the answer. So this is a typical example where a sub-agent is an optimal choice. You just want the final search result, you don't care about the process. If you use the main agent for this, the massive documentation will unnecessarily fill up your context window, which is a very valuable asset you need for more important data. And if we look at the other options, for example, option C, can you implement a custom semantic RAG solution? You obviously can, right? And you can even ask the sub-agent or give the sub-agent access to a tool that does this. However, at least at the time of this recording as well, Anthropic prefers using tools like search and grep and glob and so on to do its searches in documentations, and instead of creating a vector database with chunking and using RAG solutions and so on. So here you will be forcing Claude to use semantic RAG, which maybe it is fine, but I mean, right now, Anthropic or like Claude Code actually like uses a different way of searching in code bases and in documentations. You can just create sub-agent, and then Claude Code will be allowed to use the official tools like the bash tool or grep tool and so on to do this task without you caring about creating some chunking and vector database and all this like hassle. Okay. Append, like option B, append the documentation directly into a custom system prompt to the main agent. I mean, this will not save the context window. Create a new skill inside .Claude skills with detailed instructions on how to perform the search process. I mean, this is still not super relevant. This will not save our context window as well, because even if you create the perfect skill, at some point you will need to search in the code base, which will clutter your context window anyway. So I mean, this is why sub-agents are the correct answer to this question, and this is what I wanted to say in this video. See you in the next one. Okay, now for question number 13. After running the system on the topic of impact of AI on creative industries, you observe that each sub-agent completes successfully. The web search sub-agent finds relevant articles. The document analysis agent summarizes papers correctly, and the synthesis agent produces coherent output. However, the final reports cover only visual arts, completely missing music, writing, and film production. When you examine the coordinator's logs, you see it decomposed the topic into 3 subtasks: AI in digital art creation, AI in graphic design, and AI in photography. What is the most likely root cause? A. The synthesis agent lacks instructions for identifying coverage gaps in the findings it receives from other agents. B. The coordinator agent's task decomposition is too narrow, resulting in sub-agent assignments that do not cover all relevant domains of the topic. C. The web search agent's queries are not comprehensive enough and need to be expanded to cover more creative industry sectors. D. The document analysis agent is filtering out sources related to non-visual creative industries due to overly restrictive relevance criteria. Okay, so this question is extracted from the official Anthropic exam guide document. So let's use it as a chance to dive deeper into using sub-agents in the Claude Agent SDK. However, again, it is important to know that this actually is a very simple question. So this just gives you some idea about that the exam actually has some simple questions and some more complex questions. But this one is obviously simple, and I think you already know the answer. But let's cover some more about sub-agents in the context of the SDK, not in the context of Claude Code. Okay, so again, this is a documentation like link. Overview. So you can create sub-agents in 3 ways. One of them is programmatically. So you use the agent's parameter in your query options. So we will see an example for that. You can also use file system based like sub-agents. So you can define agents as markdown files in .claude/agents directories. So this is very similar to what you do for Claude Code. But however, here we are talking about the SDK. So I mean, you can use this file system based sub-agents in the 2 like categories. And also, as we said before, we have built-in general purpose. So Claude can invoke the built-in general purpose sub-agent at any time via the agent tool without you defining anything. Okay. So this is an example. So note that we have the agent's key in the Claude agent options, which is given to the query. Note also that one of the allowed tools for the parent agent is called agent. It was called task before, but got renamed. So I mean, here we define our options like we did before. So you have Claude agent options, right? You have allowed tools, and you have this agent tool. Previously it was called the task tool, but now it's called agent. And then you can define the agents right here. So you have, this is a dictionary. You have one agent called code reviewer, and the value is agent definition. You give it a description, you give it like a prompt, you give it some tools, and you give it a model. So this looks very, very similar to the like agent.md file that we covered in a previous video. However, we are now giving the same information roughly programmatically here. And then you have another agent called test runner, again another agent definition, description for that agent, and then prompt, and then tools. Okay, so this is how you define the agent programmatically, and again you need to allow this agent tool. Okay. So instead of defining agents programmatically, you can also create .Claude agents, similar to how you do it when using Claude Code. Programmatically defined agents take precedence over file system based agent with the same name. Okay. So again, this is a comparison about what the sub-agent receives versus not receive from the documentation directly. So the sub-agent receives its own system prompt, agent definition.prompt, and the agent tools prompt. So, I mean, if you see here, this prompt right here is injected or ingested into the sub-agent's prompt. So this is the sub-agent's prompt, okay? And also the main agent or the orchestrator agent will also like append some stuff to the prompt, asking it to do exactly what it wants to do. Okay, so it receives that. The sub-agents also receive the project claude.md. We'll talk more about this file later on actually. It also receives the tool definitions inherited from parent or the subset in tools, but it does not receive the parent's conversation history or tool results. It does not receive preloaded skill content unless listed in agent definition.skills. So I mean, in agent definition you can also add skills. It does not receive the parent's system prompt. So sub-agents can have restricted tool access via the tools field. If you omit this field completely, agent will inherit all the available tools. If you specify tools, agent can only use the listed tools. Okay. So it is beneficial to know the difference between using sub-agents with Claude SDK versus sub-agents with something like LangGraph. In LangGraph, you create the workflow, so you have more explicit control over the routing. You define the graph, you can deterministically ensure that a sub-agent is called, because you actually define that if I am in this node and this happens, please go to that node, and that node actually has a sub-agent, right? With Claude Code or the Claude Agent SDK, you can strongly suggest that Claude uses an agent in your prompt, and also by putting a magic word in the agent like description. So that word being proactively, I mean, this is explicitly like written in the documentation by Anthropic, that if you write proactively use this model or proactively use this agent when something, this gives a strong hint to the system to use this agent or this model. So this is explicitly suggested by Anthropic. I mean, this word proactively used, this is explicitly suggested by Anthropic. Okay, now for the question again. What is the most likely root cause where you have like a couple of different agents and sub-agents and a coordinator, and then the result is not exactly what you would like? So when you examine the coordinator's logs, you see it decomposed the topic into 3 subtasks: AI in digital art creation, AI in graphic design, and AI in photography. So it is actually clear that the coordinator actually decomposed the topic of the creative industries into 3 different things, but all are roughly about visual stuff. So the problem is really in this decomposition. The problem is not in the reporter sub-agent or in the web search sub-agent. And this means the correct answer to this question is actually B. The coordinator agent task decomposition is too narrow, resulting in sub-agent assignments that do not cover all the relevant domains of the topic. So you really need to do some improvements to how the coordinator decomposes the bigger task. And this is really it. See you in the next video.